The questions are asked through the Teams chat?
No, to the live chat. There should be also a chat over there.
In the sharing link?
Yes,
what,
in the
what
sharing.
do we need Teams for?
You don't need Teams. This is why you do not need Teams. You just need the link that I sent yesterday to you.
Okay, for the co-share.
Yes.
No Teams.
Yeah. Okay, good morning everyone. My name is Dr. Elena Goy and I'm a research fellow at the Institute of Photonic Chips in the University of Shanghai for Science and Technology. It is my pleasure to welcome everyone to the Photonics and Advanced Intelligent System Conference. This conference focuses on artificial intelligence-driven photonic systems and optical technologies in general. This event is organized in partnership by the Institute of Photonic Chips in the University of Shanghai for Science and Technology and Wiley journal Advanced Intelligent Systems. Before starting with the session, we will hear the opening remarks from Professor Minggu and Advanced Intelligent System editor Huan Wang. Professor Minggu is the leader and director of the Institute of Photonic Chips, is also an executive chancellor of the University Council in the University of Shanghai for Science and Technology, a fellow of the Australian Academy of Science, and a fellow of the Australian Academy of Technological Science and Engineering, as well as a foreign fellow of the Chinese Academy of Engineering. So please, Professor Minggu, you can start your remarks.
Okay, thank you, Alina. Good morning, good afternoon, and good evening. Hello, everyone. My name is Minggu. I'm co-chair of this conference, Photonics and Advanced Intelligent Systems International Conference. I'm also a professor at the University of Shanghai for Science and Technology and the director of Institute of Photonic Chips. So first of all, I would like to welcome all of you online and offline participants. Welcome to this conference. To begin with, I would like to extend my warm welcome to all of you on behalf of the University of Shanghai for Science and Technology. USST was founded in 1906 and has a long tradition of openness and collaboration. This year, USST celebrated its 115 years anniversary. In these 115 years, USST has been steering steadily towards a highly impactful university in science and technology. Photonics is one of such a field at the USST. So Institute of Photonic Chip is very proud of being the host to organize these events. IPC is an innovation-driven institute established early this year at the USST, aspiring to develop a cutting-edge technology at the interface between the photonics and artificial intelligence in order to make our future better. So this conference won't happen without a joint effort of Wiley and IPC. So I would like to take this opportunity to thank Wiley for initiating this conference, promote it through the Wiley channels, provide an online platform for this conference. Advanced Intelligent Systems is Wiley's multidisciplinary open access journal covering fundamental and applied research in the field ranging from pure science to engineering, and has been promoting the development of the topic intelligence photonics, which is the focus of this conference. I would like to also thank the steering committee and the program committee composed by international members, the plenary speaker and invite speaker for your contribution. My heartfelt gratitude goes to the local organizing committee, particularly to Elena Goy for her hard work and well-organized program. More than 300 participants' attendance is strong evidence for her team's great effort. I sincerely hope through this platform and conference, we can promote extensively the exchange and collaboration between us and enhance our friendship, particularly during the global pandemic. Finally, I would like to wish this conference very successful and thank you for your participation. Thank you.
Thank you very much, Professor Gu, for your opening remarks and for your kind words. And now we will hear from Dr. Huang. Dr. Huang studied physics at the University of Troyes in France, where she obtained a PhD for her research in the field of optics and nanotechnologies. Then she was postdoctoral fellow at Tsinghua University in the field of topological insulator and plasmonics. Huang is currently an editor of Advanced Intelligent Systems and Advanced Functional Materials at Wiley.
Thank you, Edna. Okay, good morning, good afternoon, and good evening, everyone. I'm Huan Wang, an in-house editor in Wiley. It's my great honor and pleasure to attend this exciting international conference, Photonics and Advanced Intelligent Systems, co-hosted by University of Shanghai for Science and Technologies and Wiley. On behalf of Wiley, I would like to thank for the support from Professor Minggu and the Institute of Photonics and Chips. Also, I'd like to give my special thanks to Editor-in-Chief of Advanced Intelligent Systems, Hakim, Deputy Editor, Babak, the organizing committee team, Elena from USST, Daisy from Wiley, the entire speakers today, and the friends who have given us tremendous support. Wiley empowers researchers, learners, universities, and corporations to achieve their goals in an ever-changing world. For over 200 years, we have been helping people and organizations develop their skills and the knowledge they need to succeed. We develop digital education, learning, assessment, and certification solutions to help universities, businesses, and individuals move between education and employment and achieve their ambitions. By partnering with learned societies, we support researchers to communicate discoveries that make a difference. Our online scientific, technical, medical, and scholarly journals, books, and other digital content built on a 200-year heritage of quality publishing. Wiley is also the world's third largest scientific research publisher, with more than 1,700 journals and more than 8 million articles online, meaning Wiley has a global academic publishing network with worldwide influence. What's more, Wiley is an experienced publisher in close cooperation with more than 800 societies, institutes around the world. The co-published journals account for more than half of the journals published by Wiley. It can be said that cooperation is in Wiley's genius, and what Wiley is committed to establishing long-term relationships with strategic partners and to growing together with them, as well as helping them succeed. Drawing on Wiley's international scientific research publishing experience, we provide our partners with a series of publishing services and publishing strategies to facilitate the development of our partner journals. Here, our very first successful partner journal is InfoMed, in partnership with the University of Electronic Science and Technology of China. The agreement was signed in 2017, and the first issue was published in early 2019. It was indexed in ESI in May of 2020, and SCIE in November of the same year. InfoMed has 2020 impact factor of 25, released by GCR 2021. Regarding today's conference focused on photonics and intelligent systems, I would like to announce the exciting news. The journal Advanced Intelligent Systems has been promoted to the SCIE and will receive a journal impact factor in 2021 GCR release. The journal will be indexed in the subject categories of automation and control systems, computer science, artificial intelligence, and robotics. Since May 2019, Advanced Intelligent Systems published 31 issues, 420 articles, times cited 1,683, the data from Web of Science. Overall, Advanced Intelligent Systems is Wiley's multidisciplinary open access journal covering fundamental and applied research in fields ranging from pure science to engineering, including but not limited to robotics, artificial intelligence, machine learning, automation, human-machine interaction, control systems, smart materials, and self-assembly Advanced Intelligent Systems publishes cutting-edge research selected through a strict and fair peer review process and presented using highest quality production standards to create a premium open access journal. Finally, I'm grateful to Professor Minggu and all attendees of this conference. I'm sure your exchanges of thoughts will be fruitful and rewarding during this event. Looking forward to spending more time with you. Thank you all.
Thank you very much, Dr. Wang, for your kind words, and thank you again, Professor Gu and Dr. Wang, for opening this event. I'd like to, before moving on to the sessions and to the talks, I'd like to remind everyone that this conference is also hosting a poster session. All the posters are visible at the link that you can find in the live chat or on the Wiley WeChat account. And during the closing ceremony, we will announce the winner of the poster competition and we will award the winners. So now we can move on with our first session of the day. And I'd like, therefore, to welcome everyone to the Optical AI System sessions. Once again, I am Dr. Elena Goy, a research fellow of the Institute of Photonic Chips in the University of Shanghai for Science and Technology, and I will be the chair of this session. The Optical AI System session will focus on integrated photonic platforms and devices, inference and in the nanophotonics, optical communications, and also topological photonics. I will now briefly explain the rules of the session. So I will briefly introduce every speaker and give a background on he or she. Then he or she will deliver a talk which will be approximately 15 minutes, and I will notify them if the time limit is exceeded. At the end of the talk, there will be a time for questions and answers, and all the audience can ask the question by writing them directly in the live chat that you can find on your portal. And I would like to remind everyone that when they are not asking questions or not presenting, if they can mute their microphones. So now we will start the session with our plenary talk, which will be delivered by Professor Rajesh Menon. Professor Menon is currently an associate professor in the School of Electrical and Computer Engineering at the University of Utah. Professor Menon pioneered several technologies that allowed far-field optics to be manipulated and imaged with nanometric resolution. His research direction is at the intersection of optics and nanotechnology, focusing on extending the spatial resolution of optics to the nanometer scale and the application of optics in energy. For today's event, he prepared a recorded contribution with the title Imaging and Interference with Nanometric Flat Optics. At the end of the talk, there will be no opportunity to ask him directly questions, but you are very welcome to contact Professor Menon directly via email. He will provide his email directly in the talk, and you can just contact him via email. So now we can start with Professor Menon talk.
She's muted. He's muted.
Hi, Professor. You are muted.
Welcome to the Paris International Conference. Let me first thank the organizers of the conference, especially Dr. Elena Goy and her colleagues, for the kind invitation to present to all of you some of the work from my lab. And let me first also apologize for not being there in person and not being live with you. If there are any questions that arise at the end of my talk, please feel free to email me. My address is down here, as well as my website, where you can find all the relevant papers. I want to first talk about the concept of flat optics. So my lab has been working on this idea of taking lenses, which, as we all know, perform a form of one-to-one mapping, where one point on the object is mapped to one point on the image. And we want to take these conventional, relatively bulky and heavy refractive lenses and turn them into single surfaces, or extremely lightweight flat lenses. We call our lenses multi-level diffractive lenses, or MDLs, which I'll come to later on. But the idea is to enable a drastic reduction in weight, thickness, and complexity. How much of a reduction is possible can be analyzed by plotting the lens weight as a function of the lens diameter. And as you can see, for conventional refractive lenses, the weight of the lens increases in a parabolic fashion, as you can see here. This is, for example, a conventional plano-convex lens. Whereas if you look at a flat lens, its weight increases dramatically slower, which means that, for instance, a lens of diameter 0.1 meters, a flat lens can be over 1,000 times lighter than a thicker refractive lens. This can, of course, be quite important for many applications. What are flat lenses? Flat lenses have been around for a very long time. Zone plates, as we all know, have been around for a century. This is an example from some work I did many years ago, where we used binary phase zone plates to achieve very, very high numerical aperture, or low F number. In this example, we achieved a numerical aperture of 1.14 under water immersion, which is an F number of 0.42. These zone plates were fabricated using electron beam lithography in these rings are made out of silicon nitride, which is on top of a silicon dioxide substrate, and there's a chromium mask to block the light outside the lens. Now, when this is immersed in water, water fills these grooves and because of the refractive index contrast between the silicon nitride and the water, one can achieve the appropriate phase shift in order to demonstrate focusing. And we can measure the point spread function of such a lens and show that the experiment, which is shown by these crosses, matches the theory, which is shown by these solid lines very, very nicely. So the crosses show the measurement under water immersion, and this green solid line shows the measurements, simulation, and they match very well. The red dashed line here shows the simulation in air. So in the presence of water, you're able to shrink the focal spot and achieve high numerical aperture. And at that time, we were using this for optical lithography, so we were able to form very small spots like that. Now, keep in mind that this thin optic here is incredibly thin. It's only a few hundred nanometers thick, is replacing something which is far bulkier, which looks like this. This is, for example, an oil immersion objective lens, which, of course, as many of you know, collects light with very large angles through the oil into the microscope objective. So that is illustrates the potential of flat lenses. But as we all know, diffractive optics have chromatic aberrations. And this has always been a kind of a really difficult challenge for widespread adoption of diffractive optics. Very recently, we solved this problem by appealing to multiple phase levels and applying computational optimization to achieve achromaticity. So let me first show you the photograph of the device. Our device is fabricated on a glass wafer. It is patterned using grayscale optical lithography in photoresist film, which is only a few microns thick on top of this glass wafer, which itself is only a few millimeters thick. And then the lens is placed on top of a sensor with a very small standoff distance, a conventional CMOS sensor, as you can see here. And this is an example video from this camera obtained under sunlight, produced about 5 years ago now. And there's no post-processing. So now here, for example, you can see that all the different colors are in relatively good focus. You don't see chromatic aberrations, and pretty good image quality is achieved with relatively high stress ratio. Now, importantly, the weight is really small. This is less than a fraction of a gram, and the thickness is, of course, less than 0.5 millimeter. And this thickness is primarily dominated by the substrate, which of course does not have any optical function. The actual device thickness is only a few microns. And this is what we call the multi-level diffractive lens. And if we look at this in a little more detail, this is an example of a visible near-infrared diffractive lens. If you can see there are lots of rings, and you can see that the progression of the rings are very different than that of a zone plate. Now, if I take a cross-section of these rings and plot the heights of these rings, you can see that they are fairly complicated. The heights have multiple levels here, and that's why it's called a multi-level diffractive lens. Now, this idea of using the way we achieve a chromatic performance is by allowing phase in the focal plane to be a free parameter, because phase is not recorded by a sensor, and I'll come back to this idea later on. But this is an idea that was extended and inspired by previous work by Frank Borowski and Joe Mate and others in the early 1990s. Now, if I take this geometric cross-section, I can convert that to a phase function using, because of propagation phase. As light passes through this device, it undergoes a phase delay, which has this particular radial function distribution, as shown by these blue graphs. And you can see that that distribution is quite different than this parabolic curve, which is what one would expect for a conventional Fresnel zone plate, and what is typically thought of as what a lens a phase function should look like. So this is a good example of where the phase function of the achromatic MDL is quite different than the expected phase function of a lens. Now, if I take such a lens and illuminate it with light, what's really interesting is that it focuses all the wavelengths of light to a point. So that's what's shown here in simulation, all the way from 450 nanometers to 1,000 nanometers. If I propagate the fields to the focal plane and take a square of the absolute value of the complex field, I get the intensity, which is plotted here. So you can see a really tightly focused focal spot in the blue, 450 nanometers, 550 nanometers, 650, 750, and 850. And these are just showing that the different wavelengths have different phase functions. So this is phase function between 0 and 2 pi of the blue wavelength. This is for the green wavelength. This is for the 650, 750, 850, and so on. They are, of course, very different because the wavelength affects the phase, but they all produced by the same geometry, which is shown here. So the same lens is able to focus all the different wavelengths to a single focal point. That's what this is showing. Now, of course, the most important thing is the experiment, which is in the paper, and I don't have time to talk about it. Now, we can also, of course, do very high numerical aperture, as I showed you before, but the high numerical aperture can also be done without appealing to the zone plate pattern. So this is an example of a large NA MDL with an NA of 0.9 designed for 850 nanometers. So in the center, it looks more or less like a zone plate, and you can see these beautiful structures. But as I get closer to the edges, you see these hierarchical structures where you see these larger scale structures carrying these smaller scale structures as well. And in this case, the smaller structures were about 0.45 microns, and the height total, the maximum height is about 1 micron. And importantly, we can measure the point spread function of such a lens and show that it shows very, very tight focusing. This is an example of a spot size of 0.56 microns and shows very high MTF performance as well. Now, we are, of course, agnostic to the wavelength. We can demonstrate this in any wavelength band. This is an example of a flat lens demonstrated in the long wave infrared band from 8 microns to 14 microns. This is a relatively high NA, 0.45, relatively large diameter, 15.2 millimeters. So you can see the pictures of the lenses here. It's assembled with either a Seek thermal camera attached to a cell phone, or it can also be used with the FLIR TAV2 camera. So we can take all these interesting pictures with pretty good resolution as well in the long wave IR. Very recently, we also showed that you can make this in completely in silicon. So this is etched silicon, what we call a monolithic all silicon device, which has a weight reduction of almost 2 orders of magnitude compared to an equivalent refractive lens, zinc selenide lens. And you can see pictures of this. And here you can see the lens, which is then mounted onto this FLIR TAV2 camera. And we get pictures which look like this. And with a little bit of image processing, deconvolution, we can get very clear images, which are of course comparable to what one could get from a zinc selenide refractive lens, which is almost 2 orders of magnitude heavier. These measurements were done in collaboration with Northrop Grumman. And of course we can do videos, and this is an example of a hot soldering iron. And you can also see the colder handle, of course. So you can see all the detail with very nice image quality. Very interestingly, we can actually apply these techniques to show extremely large bandwidth. This is an example of what today is the world record in terms of bandwidth, where we get a single lens, we were able to focus from 450 nanometers, which is in the visible, to 15 microns, which is in the long wave IR, with this one lens. So here we're showing just example images. So a picture of a toy car in the visible. This is the same lens, but with the image is taken in near infrared. It's the same lens, but the image is now taken in the further infrared, 1 micron to 14 micron. And here's the same lens taken in the long wave IR, 8 microns to 12 microns. So you can see different objects can be taken with the same lens, but different sensors, and it's a single optical path with very, very nice image quality. We also shown that you can scale this to very large areas, which could be important for astronomical and telescope applications and so on. So this is an example of a 100 millimeter diameter lens made on a 6-inch glass wafer with a focal length of 200 millimeters, so an f2 lens, designed for the full visible band, 400 nanometers to 800 nanometers. And here it's just showing focusing white flashlight, which shows very nice focusing with no chromatic aberrations and a spot size of about 2 microns, which is an incredibly high concentration factor of something like 2.5 times 10 to the 8x in terms of geometric concentration. Now, we can do imaging with this. This is an example measurement of the point spread function of this lens at 450, 470, all the way out to 650 nanometers. We can compare this to a conventional refractive planar convex lens, which of course is not achromatic. It's only designed at one wavelength, 588. As you go away from the wavelength, it's no longer focused. So you get a lot of chromatic aberration, and you get a pretty nice point spread function measurement compared to the refractive. Now we can take this outside and take pictures of the moon, for instance. This is something we made. It's not a telescope, it's just a photograph of the moon. We can also combine this with the refractive lens. So in this example, we took the MDL, combined it with a conventional lens, and then we can build a Keplerian telescope with this, and we can take pictures of the resolution chart. Again, very, very, very nice with no chromatic aberration. You can take it outside and take pictures of the moon and so on. Since then, we have also shown that you can do very large extended depth of focus. In this example, we made a lens which showed a depth of focus ranging from 5 millimeters to over 1.2 meters. So let me try to explain what that means. So if I take this lens and illuminate with the beam, it focuses the light about 5 millimeters away from the lens to a spot size of 12 microns. So it's a relatively small spot. The wavelength is 850 nanometers in this case, which you can see here. But it remains in focus all the way out to 1.2 meters, so slightly more than that. You can see this focal spot, of course, increases a little bit. So this is showing the radial slice of the focal spot, and this is the propagation direction of a little more than a meter. And it shows a nice tightly focused spot. So in other words, 1.2 meters away, we still have a spot size of about 0.5 millimeters. So relatively small spot. Now, in addition to just focusing, we can also use this for imaging. So we had a very large extended scene here. So our camera is here, and the lens is behind the sensor, so you can't see it. And then here there's a toy which is illuminated by a near-infrared flashlight. Here there's a small Macbeth chart also illuminated, and here there's a toy car, and there's a few other things as well. And you can see pictures of all the different things. The toy is in focus, which is about 200 millimeters away, and as you go further out, the objects are still in focus. For instance, this resolution chart is 6 meters away, so it's a really large extended depth. Now, in comparison, if you take a picture of the scene with the Google Pixel 3 camera, this is near infrared after all, and if you focus on the first toy, everything else is completely blurred. It's not an exact comparison because the numerical apertures are slightly different. Now, we are not restricted to this rotational symmetric geometry. We can make free-form MDLs as well. So this is an example of a MDL comprised of square pixels where we can form a focal spot that is square in shape. And as shown by these simulations, we can change the size of the spot and so on, and they can form some nice images. So this is an example where we can make a lens which is the same F number, which is the ratio of the focal length to the diameter, but different numerical apertures. We can manufacture these lenses using low-cost nano-imprint lithography. Is an example of one of those fabricated lenses, and these are pictures obtained from one of these lenses. We could apply these techniques to the microlens scale as well. So this is an example of a low F number visible light microlens array. Very flexible, thin films. It's about 40 microns thick and 1 centimeter by 1 centimeter. Here's a picture of one of these lenses. These are again freeform, so they're not rotationally symmetric. And you can see you can get 100% fill factor in the microlenses. The microlens pitch is 70 microns, and the focal length in this case is about 27.2 microns in air. And we can show pretty nice focusing, and I won't bore you with it, but here is showing that you form this nice square spot, and it maintains a pretty large depth of focus, which is important for this particular application, where we are trying to marry, this is used in integral imaging, where we're marrying the microlens array on a flexible substrate on top of a higher resolution print to form these three-dimensional images. And here you can see a video which shows that effect with our microlens array. Now, you may or may not know, in the United States, we use these sort of techniques for in optical document security. This is a $100 bill, which has these micro lenses paired with these high resolution prints. However, these are conventional micro lenses, which tend to be very thick, and our approach is to make our micro lenses incredibly thin, only a few microns thick. So we are demonstrating about 2 orders of magnitude reduction in thickness from what has been shown before. Now, in summary, we have demonstrated these MDLs across the electromagnetic spectrum, all the way from visible, so as examples of lenses, all the way into long wave IR and even terahertz. And these are pictures taken from all these lenses. So I actually summarized all the different lenses that we have fabricated in my lab, just in my lab, flat lenses, and tried to plot them against these plots in these axes. In the vertical axis, we have the bandwidth, which is lambda over delta lambda, which is relative bandwidth. And the horizontal axis, we have numerical aperture, which goes from 0 to 1. Of course, relative bandwidth goes from 0 to 2. So we have actually spanned all the different locations. Of course, high NA and large bandwidth is hard to do. So this is only simulation so far. So that has not been demonstrated quite yet. But we have shown relatively medium-sized NA, high NA and medium bandwidth, as well as a very, very large diameter. So the sizes of these bubbles represent the diameter of these lenses. So these lenses are very small. These lenses are very big, for instance. So this is hard to do. Now, in comparison, if you look at alternative technologies like metal lenses, they are mostly really, really small. So they are about this size or smaller. And typically, the bandwidths are also quite a bit limited. They're about in this, the metal lenses are about in this range. Now, there is some interesting physics behind why these things work, and I just want to spend a few minutes talking about it. If you think about what a lens does, is that it takes plane waves coming into the lens, and the lens simply converts into converging spherical waves, as you can see here. Now, if you think about what we actually need for imaging is if you look at the complex field in this focal plane, the amplitude has to be highly localized, but the phase is unconstrained. We don't really care about the phase because the sensor does not see the phase. So if we look mathematically at the complex field, we have A multiplied by e to the j phi, which is the phase, then the time harmonic part. Now, what's important is that this is important, but the phase is no longer important. So it can be completely unconstrained. Of course, it must satisfy the whole equation. The complex field must satisfy the Helmholtz wave equation, which means that we can take this fact that the phase is unconstrained as a degree of freedom when we do an optimization-based design or inverse design of these lenses. This is why we can design a black box-like lens, which again takes a plane wave, converts it into something more complicated, but it still nevertheless focuses to a spot. Now, I want to spend a few minutes talking about non-imaging diffractive optics as well, particularly solar concentrators and holograms. So we have also shown spectrum splitting solar concentrators, where the idea is the sunlight comes in and it separates the colors of short wavelength photons and the long wavelength photons spatially, such that different solar cells, in this case gallium arsenide, can absorb the long wavelength photons, gallium indium phosphide can absorb the short wavelength photons, and together we can get a much higher efficiency than if done otherwise. And this is an example of one of those devices. We call it a polychromat. Under sunlight, you can see the visible band over here and the infrared band, which looks very dark over there. And this is, excuse me, an example that shows you can do this with 3 bands. And we've also done electrical measurements in these papers. If you're interested in this, example, we did gallium indium phosphide, gallium arsenide, and silicon. We can also change the bands and the concentration. So in this example, we did 2 bands and a gap in between. So you can see the gap right there where there's no light. It's quite dark. There's a little bit of perturbations there. We can also, of course, do holograms, full color holograms, which work under the sun or even under the flashlight of your mobile phone. So the hologram looks translucent, but when you project an image, you can project a very nice broadband image with no chromatic aberration. It can be beautiful color images like these, as shown here, and so on. And this is just a simple video which illustrates one of these ideas where we can do a visible image with this rainbow heart, but the same image also projects this silhouette of the line in the near infrared, which of course is invisible under visible light, so you don't see that. But when you use a visible cut filter, you can see it show up. So you cut off the visible light to show up the line silhouette. So it's kind of like a secret message that can be encoded into the hologram. You can use these ideas to do 3D spatial multiplex holograms. This is an example of a hologram where we are projecting an image, but as you move further away from the hologram, the image actually changes. So the arms of the clock are rotating as you move further away. As you get closer, the arms rotate back. So one image looks like that, another image looks like that, another image looks like that, so on and so forth. Now, you can marry diffractive optics with computation. And the last part of my talk, I just want to talk about these 2 papers, which talk about hyperspectral imaging. And the idea, the working principle is relatively straightforward. We're building a camera, so we have a lens, and we have a conventional image sensor, which is shown here. And we have an object, image sensor is shown here, the object is over here, sorry. And we introduce what we call a diffractive filter array, which is a completely transparent device, but it diffracts the light in a particular fashion. So what it does is that the rays of light from one point here are focused to one point on the sensor, but they pass through this diffractive filter array and they diffract. But they diffract in a way that is wavelength dependent. So that it causes a blurring of the spot here, but the blurring is sensitive to wavelength. Now, if you know how that blurring occurs with respect to wavelength, we can actually do a de-blurring based on either linear algebraic inverse techniques or machine learning based techniques to actually extract the spectral information and thereby achieve snapshot hyperspectral imaging. And I'll just show you simple examples. So here we take a picture of a spot of a particular color, and we can extract the spectrum out of it. This is the reference spectrum. This is the reconstructed computation reconstructed spectrum for a few different colors. And here you can see the raw data and the wavelengths changing. So this is simply showing that the raw, we are able to reconstruct the channels, color channels, with something like 25 nanometer precision in this example. In the last section of my presentation, I want to talk about an even more extreme situation in the case of what if in a conventional camera we remove the optics completely and consider the signal obtained from the sensor, image sensor by itself, and pass it through some interesting deep neural networks in order to understand what the sensor is seeing. In other words, can we think about going from imaging to inferencing? Now, this turns out to be a very interesting problem. So, because if you look at the raw sensor data with no optics, it actually looks like there is nothing there at all. It looks like noise. However, that is a limitation imposed by the human brain being unable to recognize this. Now, if you train a machine learning algorithm to actually recognize the frames of video from here, it is able to interpret that video for human consumption. And indeed, it is the case by looking at the reference video, where you can see that this is what the sensor actually saw. So our experiment in this example was we took this LED array, demonstrated, incorporated a video animation, and then recorded it using the sensor. And that's what this recording looks like. And then we had a machine learning algorithm which was able to reconstruct the video from that. Now, interestingly, in the previous slide, I talked about reconstructing the image, but it turns out you can actually detect information about the image without doing reconstructions for human consumption. This, of course, we are familiar with for conventional images. In the case of, for instance, the MNIST data set, this is a handwritten digit 3. We can use a conventional deep neural network-based classifier in order to identify this is indeed the digit 3. It turns out you can do the same thing with the optic-less camera machine vision. So we have the sensor with no optics. So again, the image doesn't make a lot of sense, but we can pass it through a classifier and indeed recognize this is a digit 3. And you can do this with high accuracy as well. Now, supervised learning can work relatively well with constrained images. Our experiment in this case was we had a conventional image sensor pointing to a liquid crystal display onto which we displayed various images. In this example, we are looking at QR codes. And you can see a distance of about 1 centimeter away. And the image captured by the sensor, again, is not so meaningful to a human being. But once it passes, in this case, through a UNet, the sensor image passes through a UNet, we have the sensor image and the ground truth, and the UNet is trained to go between the sensor image to the ground truth. You're actually able to reconstruct the ground truth, the QR code fairly well. And that is shown here, where we take the sensor image, we can get, this is the target image, this is the reconstructed image, and they work relatively well. This is really cool because now you have additional privacy. It's not like if you look at it, you can't tell if it's actually a QR code or not. However, if you take a more general image like what's seen in this, this is from the data set, more complicated data set, the image is very difficult to reconstruct, as you can see by the results here. Now, in order to address this, we developed a new type of model called a self-consistent supervised model, which is recently has been accepted for publication in Optica, where the idea is that in a traditional supervised deep learning network, we are solving an inverse problem where the Y is the captured sensor image, X is the object we are trying to reconstruct. We are trying to solve this inverse problem. So in other words, if I have my sensor image, I want to learn the physics of this transformation, which takes me from Y to F of Y, and compare it to the ground truth. So this is our conventional supervised learning, which I talked about in the previous slide. In the case of self-consistent cycle supervised model, we have two networks. One network to predict the inverse problem, another network to perform the forward problem. And then you train these two networks in conjunction with each other. They're simultaneously trained and in a very special way. So let me try to explain that. So in one side of the network, we take the Y, there's a sensor image, pass it through the network F and predict the object. Then we cycle it back. You take the predicted object. Of course, we compare it to the ground truth and discriminate using a discriminator-based GAN, generate adversarial network, and pass it through the inverse. The generated image is now passed through the forward model, and which generates a sensor image, and these are compared. And these are compared on the other side. On the other side, what happens is that you take the object, pass it through the forward model, generate the sensor image, compare it to the actual experimental ground truth sensor image with the discriminator, and the generator passes back to the inverse problem to predict the object, and those are compared as well. So these two sides of the cycled networks are used for training simultaneously two different networks. By doing this, the networks are able to essentially learn the physics of the problem, and you get much better results. For example, you take the input here. This is the output of the UNet. This is a sensor input. This is the self-consistent network, and that's the ground truth. And you can see the self-consistent network, which I just talked about before, is very much closer to the ground truth, and you can see the examples compared to the UNet. And you can also think about ensembling multiple networks. In this example, we took at average the results of multiple self-consistent networks, where again we took the input, we had an ensemble prediction, and that's the ground truth. And the ensemble prediction is able to get rid of quite a bit of the artifacts and make a much better prediction, for instance, of these more complex images. And these are more quantitative evaluation of the models. So there's a single self-consistent cycle network. There's an ensemble self-consistent cycle network. Shows an improvement in the maximum average error, and this is IM, and also the peak SNR slightly. Nevertheless, the cycle consistent approach actually produces much better results than what is expected from a standard supervised learning approach. So in summary, I've shown you that this is what we do today. We have conventional lenses, we take conventional images, and we perform deep neural networks from it. Now, it is possible to modify the sensor with, for instance, the diffractive filter array, or using thin flat lenses and so on, to capture some extra information which can then be used for additional inferencing, or we can completely remove the optics and just take the sensor data and perform inferencing, which of course enhances privacy. In all these cases, we are trying to essentially reduce size, weight, power, cost, and enhance privacy. And one can also think about non-human cameras. So we're moving, in a sense, from imaging, which is very human-centric, to inferencing, which is much more robot or artificial intelligence-centric. So in summary, I've talked about flat optics, where the idea is to, we can apply machine. I didn't talk too much about applying machine learning to do the design of the flat optics, but there's quite a bit of very exciting work there. But the idea is to make lighter flat optics, which can cover larger bandwidth than conventional optics, produce larger depth of focus, can also do very interesting things like holograms and structured point group functions. Yeah, you can also think about non-imaging flat optics, which can be used for spectral control, for spectrum splitting solar concentrators, light redirection, very thin form factors, etc. Finally, you can combine diffractive optics with computation to do hyperspectral imaging. And of course, at the very end, I talked about removing optics completely and just relying entirely on deep neural networks in order to do inferencing. So lots of very exciting work in these areas right now. So for those of you who are coming into the field, this is a very, very exciting time in the field of both optics and AI. Let me end by thanking all the wonderful students who have worked on this project over the years. There are too many of them to name here. I also must thank various collaborators from various institutions, as well as many funding agencies who have supported work in my lab. Let me thank you all for the kind invitation and for your attention for listening to my talk. And I'm going to end by advertising some PhD fellowships that are available for those of you who might be looking for positions who are interested in going on this research journey with us. Please take a look at our website and feel free to contact me if you're interested. Thank you very much, and I'm more than happy to address questions via email. So please be in touch and take care. Hope all of you and your families are safe. Bye-bye.
Okay, so we'd like to thank very much Professor Menon for a very comprehensive presentation on the nanostructured flat optics and the application of this system in imaging, holography, and also deep optics, where these flat optics elements are combined with the sensor for executing computations and inference. As Professor Menon already said, if you have any questions for him, you can just directly contact him through his email address that you can find here, or you can just look for his name on Google or in his institution and just contact him directly. He will be very happy to answer all your questions. So now we move on with the second talk of this session. The presenter in this case is Andrea Blanco Redondo. Dr. Blanco Redondo is the head of Silicon Photonics department of the Nokia Bell Labs in the United States. There, she established new concepts and applications for nonlinear integrated optics and quantum topological photonics. Before that, from 2015 to 2019, she worked at the School of Physics in the University of Sydney in Australia. And in 2018, she was an Optical Society ambassador. In 2016, she won the Optical Society of Australia Geo Award. And before that, in 2014, she won the Spanish Ada Byron Top Female Scientist Award. So for today, she prepared also a recorded contribution with the title Topological Quantum Photonic. In this presentation, she will just show us and present her own work in the field, as well as provide a perspective of the impact of artificial intelligence on topological photonics and vice versa. So now we can just listen to her video.
Hello, my name is Andrea Blanco Redondo from Nokia Bell Labs in New Jersey in the US. First of all, I would like to thank the organizers and the chairs of this conference for putting together such a nice program and for inviting me. I'm really sorry I cannot be there with you live because of the time difference, but I would be very happy to respond to any questions you may have if you send me an email, so please do. Also, I would like to acknowledge my collaborators. I'm going to touch on a few topics today, so it's a long list and I'm very grateful to all of them. All right, so since I'm going to be telling you about topological protection of quantum states, let's start by discussing what topology is. Topology is a branch of mathematics that deals with quantities that cannot be changed under continuous deformation. It's especially easy to see in geometric objects in which the topological invariant is the number of holes, also called the genus, which is directly related to the Gaussian curvature of the objects. That's why we say that, say, a donut and a mug are topologically equivalent. However, a ball and a donut, or a donut and a teapot, are topologically different, topologically distinct. And it's quite interesting what happens at the transition between two topological classes. Now, while geometric objects have topologies in the real space, photonic systems have topologies in the momentum space. So more specifically, the topological invariant of photonic systems are related to the Berry curvature of the bands of the dispersion relation of these photonic systems. Now, what is interesting is that these topological invariants can only take integer values, and that and the interface between two systems with different topological invariants, as we represent here schematically, there can be edge states that live at the interface between these two topologically distinct materials and that are very robust to fabrication imperfections and other type of disorder. And that's what we try to leverage in topological photonics. The field of topological photonics has been going strong for over a decade already. There's been a lot of different experimental platforms proposed. I don't have time to touch on all of them because this is a short talk. So I'm just going to focus on the platform that we've been using, which is basically a one-dimensional platform with chiral symmetry. And I'm just going to go into more detail about that. This is a general representation of the platform that we use in most of our experiments. It's based on the SSH model, which is basically the simplest topological model, and it's based on this alternate strong weak coupling between sites. It's been implemented in different systems before, but our system is basically an array of silicon waveguides that are strongly coupled to each other. So what you can see here is that depending on how we choose the unit cell, we can have a topological invariant different than 0 or a topological invariant of 0. So of course, at the interface between two regions with different topological invariants, we're expecting a very robust electromagnetic edge mode. To explain this a little bit further, let's relate to a system that may be more familiar to most of you. Let's think of an array of equidistant silicon waveguides. If you think of the energy diagram of a structure like this, with, in this case, the energy is embodied by the propagation constant of each of the supermodes of the lattice, you can see that in the case of equidistant waveguides, all the modes would be extended in the lattice, right? So therefore, there's no band gap here, and the energy diagram would look something like this. Now, if you start transitioning from this situation in the left, apologies. If we start transitioning from this situation in the left to this, in the right to the situation in the left, we can see how a band gap starts opening up as we dimerize the system, as we alternate the coupling. And at the interface or at the edge of each of these lattices, we're going to have a mode that is strongly localized in the center of the band gap. What is interesting about this mode is that it's topologically protected in the sense that if we randomly vary the position of each of the waveguides in the lattice, of each of the sites, we can see that all of the extended modes change, that their propagation constant changes, but that doesn't happen to the topological mode, which remains strongly localized at the center with an unchanged propagation constant. This mode is obviously strongly exponentially localized in this interface here, and as it is specific to the SSH model, it shows this zigzag type of localizations with zeros in every other site. Or if you want to think about it in different terms, zeros in one of the sublattices. Whereas in the case of a structure like this, for example, we have no localization. All the modes are spread out. Now, what is really interesting about this platform is that because of the strong nonlinearity of the material of silicon and the strong confinement of silicon waveguides, of these nano waveguides, we can leverage four-wave mixing in the lattice to generate correlated signal and idler photons, correlated photon pairs. So four-wave mixing is a chi3 nonlinear optical effect in which basically both energy and momentum have to be conserved. So what we can do is we can basically pump our system, pump our silicon lattices with pulses that are strong enough. And in this way, we generate these biphotons, these photon pairs, and we can make them coupled to different modes. Specifically, we can make them coupled to the topological mode or the topological modes in the lattice, and we can study the robustness of the resulting quantum state at the output of the lattice. So this is basically a general overview of the kind of experiments that we're going to talk about. Our experiments look more or less like this. We are going to have mode log lasers emitting pulses. Our around picosecond pulses, around picosecond durations. We're going to pump the lattice wherever we're interested. And in this case, for example, in the center of this long defect, which is where the topological mode resides. And then at the output, we spectrally separate out signal and idler, and then we detect them with superconducting nanowire single photon detectors, and we detect the time correlations by using time correlation electronics. Right, so one of the first things we looked at is what happens to biphotons coupling to just one topological mode in the SSH lattice in silicon. All right, so what we can see is that as we increase the disorder in the lattice, and again, this is disorder in the position of each of the waveguides, there are certain features of the biphoton correlation that are preserved under even very strong levels of disorder. In this case, is the zero amplitude in one of the sublattices. And that is related to the underlying modes of the SSH lattice. As you can see here, as we increase the disorder, the propagation constant of the topological mode remains unchanged. And also, if we look at the modal amplitudes, we see that there's some variation in the amplitude of the mode in one of the sublattices, but the other sublattice remains strongly pinned at zero. We can compare this to a similar lattice that also offers localization, but is trivial localization, not topological, right? So you could imagine just an array of equidistant waveguides with a wider waveguide in the center, right? So in this case, we observe localization, but as we increase the level of disorder, we see that there's nothing that is preserved in the spatial biphoton correlation. And this is again related to the fact that this mode is not topologically protected, so the propagation constant changes upon disorder, and every aspect of the mode of the modal amplitude also changes upon disorder. Okay, so once we realize this potential that topological modes have to protect photon pairs, we extended this into a system with two of these topological modes. And what we did is we basically created spatial entanglement, as you can see here, between two of these topological modes. So the idea here is to see if basically topology can protect spatial entanglement in this photonic platform. So in these measurements that you see here, taken by my former students, Michelle and Cooper, you can see that the same signature of topological protection in the SSH model, this zero amplitude or zero counts in one of the sublattices, is maintained here even for very high levels of disorder, both in experiments and simulations. We did this again, we compared it to an entangled system with two modes that are not topologically protected with these wider waveguides here and here. And what we can see is that even when we have like 0% disorder, this means that we only have the inherent disorder of the nanofabrication. Basically the modes, the entangled state is strongly perturbed. Now, these measurements per se do not represent proof of protection of the entanglement, but what one can do at the output of this lattice is perform quantum interference of the output states. What you have here is basically simulations of how the visibility deviates from its ideal value. So being close to zero here is good because that means that your visibility remains close to 1. And what you can see in blue is what happens with this system with two topologically spatially entangled states, and in red is what happens with two trivial states that are entangled. And you can see how the topological modes remains strongly robust, strongly unperturbed with disorder, whereas the trivial case is very, very strongly distorted, even at very short levels of disorder, up to 10%. Right, so what else can we look at in this type of lattices? Well, this long defect is not the only type of interface that one can look at. We can also have something like this here. It's actually a short defect, but we still have that interface between two lattices with different topological invariants. Now, what is beautiful about this system is that on top of the topological mode that appears here at the center of the topological bandgap, there's two trivial modes that are localized simply because you have a region of higher index of refraction here. So we have three localized modes, and it turns out that these 3 localized modes are co-localized. They all exist, say, in these 9, or in this case, we represent the 9 center waveguides, and you can see here how both the topological and the 2 trivial modes are co-localized. Now, what's interesting here is that if we generate spatially entangled, frequency and time entangled biphotons here, we can actually create spatial entanglement between these 3 modes that are co-localized, and I'll explain to you how. What we can see is that if we pump in the center, because of the shape of the modes, and because of the fact that the topological mode doesn't have any support in the center waveguide, we only excite a combination of the 2 trivial modes. And this is this beating pattern that you're seeing here with the pump. However, the photon pairs can be generated in each of the 3 modes, the topological or the 2 trivial modes. And that can be explained theoretically. I don't have time to do it here, but please email me if you're interested in how this happens. But you can already see here that in this case, the beating pattern looks different, and that we start having some more signatures of the topological mode here. And you can see this more clearly once we actually look at how basically the quantum states looks at 3 different points of the lattice. So this is A, B, and C. So at the beginning and 2 points close to the end of the lattice. We can see how the quantum states actually change quite a bit with the propagation distance, as we would expect here. And if we perform the overlap of each of these biphoton correlations with the eigenmodes of the system, the biphoton eigenmodes, we can see that at the beginning, we don't have any biphotons in the topological mode, but as we move to longer propagation distances, the topological mode becomes more populated, and also the trivial modes, showing this entanglement between the 3 trivial modes. And in particular, what is interesting here is that we have entanglement across 2 different topologies, and that is actually quite novel and quite interesting. These are the measurements, again, experiment here for different levels of disorder and simulations. One thing that you can already see here is that actually the entangled state is not robust to disorder, and that happens also in the simulation, so this is not related to any experimental issue. Why is this? Well, if you have a look at the energy as a function of disorder, as we have here, as the disorder increases, basically, the band gap related to the trivial modes actually closes. And not only that, but as we increase to even higher levels of disorder, there are other localized modes, trivially localized modes that appear, right? And they mix up with the system. That's really what is changing the output at different levels of disorder. Now, we can do something similar to what I showed you before. We can basically calculate the overlap of each of the quantum states at the output of the lattice with the different eigenmodes. And what I can show you is that whereas the population of the topological modes remains quite flat with disorder, the population of the trivial modes descends quite rapidly. So this tells us that as we move to larger and larger levels of disorder, the population of the topological mode would end up actually prevailing. So this is, again, an interesting way to basically engineer the weights of the different topologies within that entangled state. And just to finish, there's this interesting thing that we've been looking at lately, which is basically the localization of biphotons in sinusoidal waveguide arrays. This is not topologically protected, but nevertheless, it also shows some level of robustness. So what I'm showing you here is what happens when the amplitude of the curvature is at a critical amplitude that is a particular value that depends on the parameters and also on the wavelength, and what happens when we detune from that critical curvature. So what you can see here in the experiments, for example, is how if the critical curvature is changed by 10%, the output state remains quite similar. So it's quite robust to some changes in the curvature. But as we deviate more and more, for example, 20% from the critical curvature, we can see how the biphotons start basically spreading across the lattice. So this is actually quite interesting and quite new, and there will be more on this coming. This is quite preliminary. And that takes me to the end. Thanks so much. Please do send me questions, and have a good rest of your day. Thank you so much.
So we would like to really thank once again Professor Andrea Blanco Redondo. She really delivered a very inspiring and a very good introduction on topological photonics, and she presented her work on multiphoton quantum state and biphoton entanglement. As she mentioned just at the end of this talk, if you have any questions for her, just feel free to contact her directly via email. And now we will move on with the third speaker of our session, Dr. Zibang Zhang. Dr. Zhang Zibang is currently an associate professor in the Department of Optoelectronic Engineering in Jihan University. His research areas include single pixel imaging, three-dimensional imaging, high performance and low-cost microscopes, and artificial intelligence. The technology that he developed during his career provide new ideas for computational imaging and substantially expand the application fields of single pixel imaging technology. You can start whenever you are ready, Dr. Zhang.
Okay, thank you, Elena, for your kind invitation and introduction. Good morning, ladies and gentlemen. I'm Zhang Zibang from Jinan University, Guangzhou, China. I'll be talking about an object classification method which aims at fast-moving object classification. And the method is implemented in a manner where no cameras are involved, no images will be taken, and no imaging is needed. The device used for light signal detection is only a photodiode, namely a single pixel detector. So the title of my speech is Imaging-Free Classification of Fast-Moving Objects based on Single Pixel Detection. My talk is organized as follows. First, I will give you a brief introduction about object classification. Object classification is a technique that is used to classify or predict the class of a specific object in an image. The main goal of this technique is to accurately identify the features in an image. Object classification is also known as object recognition. Object classification has found various applications ranging from face recognition in identification, online inspection in industry, automated diagnosis in biomedicine, vehicle recognition in public transport. Even the laptop I'm using uses face recognition to unlock. In a word, object classification is a widely used technique. But how does object classification actually work? We first consider object classification by human vision. For human vision, the cornea and the lens allow the target object to produce a clear image on the retina. The information from the retina in the form of electrical signals is sent via the optic nerve to other parts of the brain. The brain ultimately processes the image and allows us to see and understand what it is in the image. However, the visual processing mechanisms are not yet completely understood. Recent findings from anatomical and physiological studies in monkeys suggest that visual signals are fed into at least 3 separated processing systems. One system appears to process the shape of the target object. A second appears to process mainly about color. And third appears to process movement, location, and spatial organization of the target object. From this perspective of view, human vision relies on the feature information of the target object. Let's see object classification by computer vision. It is very similar to that by human. A camera is used to capture the image of the target object, and the resulting image is processed and analyzed on a computer through certain algorithms. There are quite a lot of algorithms having been reported for object classification, such as minimum distance to mean, maximum likelihood, k-nearest neighbors, support vector machines, multi-layer perceptrons, and convolutional neural networks. No matter which algorithm is used, the overall workflow of object classification by computer vision can be summarized into 4 different steps. And the most significant and tricky step is extracting, that is feature extraction, because it is the feature information that object classification relies on. With the advent of deep learning, machine vision can perform better classification than human vision since 2015. However, there are still some challenges in object classification. One of those challenges is fast-moving object classification. Fast-moving objects would result in motion blur in the image captured. Severe motion blur would lead to failures in feature extraction, resulting a wrong classification result. High-speed photography is an effective approach to suppress motion blur, but it is very costly. In addition, high-speed photography is not preferable for long-duration object classification because it generally generates a huge amount of data. Another effective approach is image post-processing. But image post-processing generally takes a long computational time, so it is not preferable for real-time object classification. So how to achieve real-time and long-duration fast-moving object classification remains a challenge. Currently, most object classification approaches in computer vision are imaging-based. This imaging-based scheme consists of 2 steps. The first is image acquisition, and the other is feature extraction. But it turns out it is actually of a low efficiency in terms of data, because the object classification relies only the feature information, which is only a small portion of the information provided by the complete image. A lot of image data are discarded in the process feature extraction, as storage, bandwidth, and computational capacity are limited. Real-time and long-duration fast-moving object classification turns out to be difficult. So is there an approach which acquires only the feature information instead of the complete image? Here we report an imaging-free approach. This approach doesn't need to acquire a complete image and even needs no camera at all. The key to the approach is a optoelectronic convolutional neural network. In this network, the convolutional operation is implemented by using structured illumination and single pixel detection. Here, a photodiode is used as a single pixel detector to collect the light signal from the target object under structured illumination. To demonstrate this approach, we designed this network for classifying fast-moving handwritten digits. We use the handwritten digits images provided by the network MNIST. Please note that the size of the image provided by the database is 28 by 28 pixels. In order to achieve optical convolution. The convolution layer is designed in the same size as the training images. As a result, the convolution operation will be degenerated into inner product, and which can be achieved by using structural illumination and single pixel detection. To improve the robustness of the network against motion, we apply random rotation and lateral shift to the training images. The CNN is then trained by using the training set. After the training, the feature of the moving handwritten digits are condensed in the convolutional layers. Here shows the resulting 15 convolutional kernel patterns from the trained CNN, and we will use these 15 patterns to generate structural illumination to the target object. To achieve object classification, we use a spatial light modulator. Here shows a projector to generate and project the convolutional kernel patterns on the moving objects. And a photodiode is used as a single pixel detector to collect the backscatter light. And the resulting signals are fed to the feature map of the CNN. Here you can see the convolution operation is implemented by an optical way. We validate the proposed approach experimentally. Here is our experimental setup. You can see the handwritten digits are printed on films and they are mounted on a motor-driven disk. We use a digital micro mirror device, DMD, as a high-speed projector to generate and project the convolutional kernel patterns on the fast-moving handwritten digits. Single pixel detector that is actually a photodiode collects the transmitting light. We know that DMD is a high-speed spatial light modulator, but it can generate binary patterns only. Actually, the convolutional kernels pattern we use are multi-grayscale. How to solve this problem? We attempt to solve this problem by using a strategy called upsampling and fit dithering. The binarized pattern you can see here can well approximate the originally multiple grayscale pattern. Moreover, the signal-to-noise ratio is an important factor in accurate object classification. Therefore, we propose to use differential measurement. Specifically, one pattern is projected followed by its inversion. As such, we have two single pixel measurements for each convolution kernel pattern. Then we subtract these two single pixel measurements to derive a so-called effective measurement, and we fit the CNN with the differential measurement. We also know that with the differential measurement strategy, the total pattern number is doubled. Here shows the raw single pixel measurements for different object motion speeds. You can see the ups downs here are corresponding to the light intensity. By changing the input voltage of the motor, we can control the linear speed of the handwritten digits. As you can see from the results here, when the linear speed is 3.61 meter per second, the network can achieve the classification accuracy at 100%. Reasonably, as the speed increases, the accuracy decreases accordingly. Even the linear speed is up to 9.5 meter per second. the accuracy is still above 60%. We also note that the DMD reflection rate in our experiment is 17,000 Hertz, and it can achieve a field of view with 45 millimeter by 45 millimeter, and the temporal resolution is only 5 millisecond, 1.6 millisecond for data acquisition and another 1.4 millisecond for computation. In other words, we just spend 3 milliseconds for each classification. And the data throughput of the whole system is very small. You can see the whole system only generates 0.95 megabytes per second. So the whole system is suitable for long-term, long-lasting object classification. In summary, we report a imaging-free, fast-moving object classification method, which is based on a optoelectronic hybrid convolutional neural network. The proposed method uses spatial light modulation and single pixel detection to achieve optical convolution, and it allows to capture the feature information directly. The proposed method is applicable for real-time and long-duration classification. And as the single pixel detectors can work at wide broad waveband, so the proposed method is potentially applicable for hidden moving object classification at non-visible wavebands. Okay, that is all for my presentation. Thanks for your attention.
Thank you so much, Dr. Zhang, for your introduction on object classification and also for presenting your work on imaging-free object classification with single pixel detector in the case of fast-moving objects. Now we have a few questions for you, if you are happy to answer them. So the first one is, what is the limiting factor, so the bottleneck, for the detection rate of the single pixel detection system? Is it the readout of the photodiode or is it the DMD?
At current stage, the bottleneck is the refreshing rate of the DMD. As you can see, the DMD we use in our experiment is at a rate of only 17,000 Hertz. And cutting edge of the DMD is only 22 kilohertz per second. So it limits us to project only 22 kilo patterns per second. For the detectors, we have many fast, high-speed detectors such as PMT. They can operate at a much higher speed. So here, the main factor that limits the classification rate is the spatial light modulator.
Okay, thank you so much. The next question is, how many single pixel measurements are necessary to classify one digit in this case?
Okay, in our case, we take 30 single pixel measurements for classifying each digit. Because in our case, the target object is relatively simple, so we can use a small number of patterns to classify them. But it is reasonable for some complex objects, the number of patterns used may be increased. Okay.
Okay, thank you so much. So the last question is from me. So in this case, these 30 measurements that you take in your experiment, you show that the images, they rotate on the wheel in order to simulate the fast movement. Is it so? Did you train your network to learn the direction of the movement of the digit, or is it irrelevant? So a single digit can be imaged even if it's moving, let's say, randomly, like shaking or being blurry?
Yeah, it is a very good question. Actually, in our experiment, we only simulate the fast-moving digits by using a motor-driven motor, and we actually have considered this issue. So in the training process, we add some random rotation and lateral shift to the training image. As what you ask, we can add lateral shift along different direction to the training image to add robustness to the system against any motion of the object.
Okay, thank you very much for your presentation once again, and also for taking the time to answer the questions. And so now we will move on with our next speaker for the session, which is Professor Chi Nan. Professor Chi Nan is currently a professor in the Department of Communication Science and Engineering at Fudan University here in Shanghai in China. Before that, she worked as an associate professor at the Technical University in Denmark, at the University of Bristol in the United Kingdom, and later on she joined the Guangzhou University of Science and Technology as a professor. Her research interests include advanced modulation methods, all optical information processing, and wireless network integration. Today, she will deliver a talk with the topic Visible Light Communications in 6G, Challenges and Prospects. Professor Nan, when you are ready, you can start your talk.
Okay, thank you. Good morning, ladies and gentlemen. It's my great honor to join the conference and give a talk. I'm very appreciated for the invitation from Professor Gu and Dr. Elena. The talk of my presentation is Visible Light Communication towards 6G, Challenges and Prospects. Here is the outline. First, I will give you a brief introduction on background and motivation, and then I will introduce the fundamentals of visible light communication, the challenges and the future perspective, and finally, the conclusion. Well, 6G has drawn more and more attention in research community. One of the most remarkable demands is the intention from connecting everything to connecting intelligence. The requirement of bandwidth can be 1,000 times of 5G. How can we achieve this target? Because the radio frequency spectrum has been exhausted by 2G, 3G, 4G, and 5G. So people have to think about higher frequency spectrum. For example, terahertz communication.
Professor Chi, I would like to let you know that the slides is not in the presentation mode.
Okay.
Yes, if you can do it, if you can launch the presentation mode or manually rotate the slides. Thank you.
So how about now? Is it okay?
Yes, now we are,
Okay.
yes, we read the research motivation and now the research motivation of 6G, yes.
Yes, okay.
Thank you so much.
Okay, thank you. So what is visible light? The light is visible to human eye. The wavelength is from 380 nanometer to 760 nanometer. And the frequency is about 400 terahertz to 800 terahertz. Visible light communication has many advantages. The white light is safe for human eyes, and there is no electromagnetic interference. Currently, the spectrum license is free, and it is suitable for security communication. This picture shows the application scenarios. We can use street light for hotspot, and we can use traffic lighting or car headlighting to realize vehicle-to-vehicle communication. For indoor illumination, we can do indoor communication and navigation. And maybe in the future, up close, can realize wearable LED communication. So how about 6G networks? When we consider 6G future network, it consists of 3 different networks. The first one is space-sky network, and the terrestrial network, and the underwater network. People are always talking about the terrestrial network. In this talk, we will pay more attention on space-sky network and underwater network, and we will see that visible light communication has great potential in these 2 specific networks. The first one is space network. Space network is organized by satellite. Visible light communication has great potentials in inter-satellite communication. It can achieve geo network, MEO network, and LEO constellations. We can also realize the communication between different orbits. Visible light has shorter wavelengths compared to infrared wavelengths. So in general, it has good beam quality because lower wavelengths means small divergence angle and long transmission distance. And visible light transmitter is usually based on gallium nitride. This kind of semiconductor has good radiation performance, about 1,000 times higher tolerance to the radiation intensity compared to infrared. So for underwater communication, usually we have 3 different ways. The first is acoustic communication. It can transmit over long distance, but at very low data rate. For radio frequency communication, it suffered from transmission loss due to the conductivity in seawater. So visible light communication may be the only way to realize high data rate transmission over a moderate distance. The typical applications about transmedia from satellite and plane to underwater objects and underwater Internet of Things, we can connect sensors, AUV and ROVs, and wire and wireless integration. To realize an UV-LC, we have 2 main different approaches. One is based on LD and the other is based on LED. For laser-based visible light communication system, underwater communication system, it can reach long transmission range, high data rate, but the laser requires precisely alignment. LED has much larger divergence angle, so we can realize point-to-point communication and point-to-multiple-point communication. This figure shows the schematics of visible light communication system. It consists of 3 parts: the transmitter, the channel, and the receiver. At the transmitter, it consists of electronic parts and optics parts. We can do coding and modulation and pre-equalization in the transmitter. And in the receiver, we can do post-equalization, decoding, and demodulation. We summarize our latest results in visible light communication system. First is the material and devices. For visible light sources, we can use LED, we can use laser diode, and we can also use superluminescence laser diode. About LED, we have 5 different types. Blue LED plus yellow phosphor and UV LED plus RGB phosphor can both generate white light. We can also use RGB LED. We can combine 3 different colors together to generate white light. New approaches based on photonic crystal LED and micro LED has been carried out recently. These 2 specific LED has much wider bandwidth. To detect visible light, we have to use optoelectronic conversion. Usually we can use a PLN photodiode. To increase the receiver sensitivity, we can use APD. Of course, we can use image sensor based on CCD or CMOS, but at a very low frame speed, about 30 second frame. This is collaboration work with Nanchang University with silicon. It's a silicon-based LED. This hemispherical and pyramidal pattern surface textured gallium nitride vertical LED can increase the light extraction efficiency, and the Argentine reflector is used to improve single-side luminescence. In order to have a better collection of visible light, we can use integrated pin array to detect the visible light. This is an example, 3x3 pin array. In this way, we can increase the receiver field of view, and we can also use maximum ratio combination algorithm to further increase the receiver sensitivity. Our previous demonstration is based on point-to-point communication. Can we increase the receiver flexibility? This is a very interesting example. We fabricate one-dimension binary black grating on top of substrate of hybrid polymer. In this way, a 70% improvement in bandwidth can be achieved by this nano pattern system. So next is high-speed system. How to achieve high speed and high spectrum efficiency is a very essential problem in visible light communication. If we look at this optoelectronic field expression, we can find we have amplitude, frequency, phase, and polarization. And in each dimension, we can realize different modulation format, and then we can increase the modulation capacity. And in each dimension, if we use multi-level modulation, we can further improve the system capacity. Research on probabilistic shaping and geometric shaping have been carried out recently to approach the Shannon limit. Probabilistic shaping is suitable for low device bandwidth and uneven frequency response. When the signal satisfies the Boltzmann-Maxwell distribution, the mutual information between the TX and RX signal can be maximized. This is our latest experimental demonstration about 24 gigabit for single LED chip. It's a silicon substrate 4x4 LED chip array, and we generate 8 wavelengths. It's a WDM system based on DMT bit power loading modulation scheme. We also demonstrate 2 gigabit per second over 20 meters for long distance application. The next one is multiplexing and networking. We simply demonstrate 2 examples. How can we realize a visible light-based local access network? Of course, we can use power line communication because every lamp will connect with electricity power line. You don't need to change anything. You don't need to implement any extra line or cable. But when the data rate of visible light communication is far more than power line communication, we have to connect every lamp with optical fiber. And this is a demonstration of network infrastructure based on fiber backbone. It has star topology. We can support 24 users simultaneously. This is a collaboration work with Huawei company. If we look at the picture on the left, this figure shows the network, the hardware infrastructure. In total, we have used 6 FPGAs. The light source is 2 silicon LEDs. The modulation format is DMT 64 QAM, and the useful bandwidth is 416 megahertz, and the overall data rate is 5 gigabits, real-time demonstration. The next is underwater VLC. Based on this 2x2 silicon substrates, LED array, we have demonstrated 20 gigabit per second UVLC transmission. We have successfully demonstrated this UVLC prototype. This prototype is realized by 9 array silicon blue LED transmitters. The receiver is based on MPPC. It has very high receiver sensitivity. We demonstrate 2 megabit per second over 100 meter underwater link and 8 megabit per second video transmission over 50 meter link. The last one is machine learning. Machine learning has been widely used in optical communications. It has many applications. For example, nonlinear mitigation, optical network monitoring, modulation format recognition, and other applications, carrier synchronizations, and phase frequency estimations. This is an example for support vector machine. Usually when we detect the conventional constellation, we usually use Euclidean distance, and we report this support vector machine-based new classification idea. It can find a hyperplane between 2 groups of data. Therefore, the data is no longer simply separate linearly. It can be separated nonlinear. This is an experimental demonstration on deep neural network. This is a GKDNN. It has 1 input layer, 2 hidden layer, and 1 output layer. Based on this additional Gaussian kernel, we can improve the training rate of the DNN equalizer by 35%, and the total data rate can be improved from 1.38 gigabit to 1.5 gigabit. In previous demonstration, we only deal with the signal processing in time domain, and we report a new idea to use STFT, short-time Fourier transform, to generate time frequency 2D image. We all know that machine learning is very powerful in image processing. In this way, we can deal with this time frequency image to improve the system performance. Okay, although over last decade, visible light communication have achieved many progress, it's still facing many problems and challenges. We summarize it into 3 different challenges. The first challenge is complex channel modeling of high-speed visible light communication system. For example, for underwater transmission channel, it will have absorption and scattering. There is no analytical solution. The second challenge is how to realize high sensitivity and high efficiency devices. For infrared devices, it has a bandwidth about 100 gigahertz, while for visible light communication, the bandwidth is only 1 gigahertz. We still have a long way to go. The third challenge, how to balance the data rate, the distance, and the signal-to-noise ratio limitation. Research directions, including space division multiplexing, AI-enabled MIMO DSP algorithm, and coherent receiver should be considered in the future. This picture is courtesy by Professor G.K. Chang from Georgia Tech. He said 6G is coming, and 6G will be an all-spectrum wireless access network. For indoor applications, we may use FSO, free space optical communication, we may use millimeter wave communication, and we may use visible light communication. For independent communication research field, visible light communication needs a new discipline. So far, we have many research on transmitters, we have many research on receivers, but we don't have modulators, external modulators, we don't have amplifiers, switchings, multiplexers, demultiplexers. So we need more optoelectronic devices. We summarize the challenges and possible solutions. In the future, visible light communication requires super high bandwidth light sources, high responsivity detectors, and MIMO communication devices and optical antenna. In conclusion, we have demonstrated 5G real-time MIMO visible light communication system, and we demonstrate 24 gigabits visible light communication based on single LED chip. Looking into the future, VLC is promising in future 6G wireless communication, in space sky communication, and in underwater communication. That's all for my talk. Thank you for your attention.
Thank you very much, Professor Nan, for your talk and for explaining so well visible light communications and the application for 6G networks. I have a few questions for you. I think we have time for those. So one question is, what's the power of the blue LED array for the 100 meters underwater communication?
Okay, the electricity power is about 40 watt. Electricity power is 40 watt, but the optical power is much less than that. We have measured it's less than 9 watt.
Okay, thank you. And why blue is the preferable wavelength based on the transmission spectrum?
It's for in wire transmission, in underwater communication, the blue and the green wavelengths has lower attenuation during underwater transmission. So that's why for underwater visible light communication, we usually use blue light and green light.
Okay, thank you. Another question is why they refer to slide 19. So why the nano patterning improve the performance? If you can expand on that.
Okay, which slides?
Slide number 19.
So let me see. I have. So what is about question?
I think that you mentioned nano patterning of a surface, and why the nano patterning is improving the performance in this case.
Okay, so if we remember this LED based on spontaneous emission, so the output optical direction is different. You know, it can output every direction. When we use this specially designed fiber black grating, we can uniform the optical direction and then increase the optical signal to noise ratio and optical beam quality.
Okay, thank you so much. The last question is from me. It is like if you can give a little bit of more insight on what are the challenges in the case of the Li-Fi. So when you mention, like even in the 6G presentation, you mentioned the communication via the light inside, so via free space. In that case, what are the real challenges to make that communication successful?
Well, so far, I still think the high speed may be the great challenge. If we remember the Wi-Fi history, the Wi-Fi is generated in last century, in 1990s. But for a long time, people didn't use Wi-Fi, they used infrared. About year 2000, they used infrared. But in year 2005, when the data rate of Wi-Fi becomes 5 megabits per second, and then almost over one night, a lot of companies produce product Wi-Fi chips and Wi-Fi applications. So I think maybe the breakthrough may be the high data rate for future meta service, you know, virtual reality, for hologram, for 3D visualization, maybe. I think in the future it will require extremely large high bandwidth, that wireless frequency communication cannot obtain such high data rate. And then we can use terahertz and we can use visible light.
Okay, I think these are all the questions that I get. Let me check if we have an extra question, which is, would optical angular momentum help in the case of the 6G? In case,
sorry, can you hear me?
Yes, I can hear you. I repeat the question. The question is, would optical angular momentum help in the case of a 6G? So considering that degree of freedom of the light signal, will that help?
Well, I'm not very clear about the question, but I think in 6G, we don't have only one technology. That is a fundamental characteristics of communication field. As we all know, so far we have Wi-Fi, we have 5G, 4G, and we have Bluetooth. So we have different choice. I think in the future 6G, we also have different many choice. They will coexist simultaneously.
Okay, thank you very much for your talk and for the presentation and for taking the time also to going through all the questions. I think that if anyone has other questions for you, they may contact you directly via email regarding your talk. And so we would like to thank you again and move on with the last. Moving on now with the last talk of the session. The last speaker is Xinyuan Mike Su. Dr. Su is currently working in Arthur Lowry's research group at Monash University in Melbourne, Australia. He is one of the few recipients of the EEE Photonic Society Graduate Scholarship, and he published a multitude of research articles, including articles in Science, Nature, and Nature Families journals. His current research interests are integrated neuromorphic optics, microcomms, and microwave photonics. Due to an unforeseen event, Dr. Su is not able to deliver a live talk, but he actually sent a video contribution that we are going to listen to now. And the title of his talk is Ilenen Tops Photonic Convolutional Neural Networks.
Everyone, my name is Xinyuan Xu from Monash University. Today, the topic of my talk is photonic neuromorphic hardware accelerators based on microcomms. My talk will be given by 4 parts. First, I'll introduce the background of optical neural networks. Then I'll talk about the teraops speed convolution accelerator based on time wavelength interleaving. Thirdly, I'll talk about the optical convolutional neural network that we've demonstrated. And finally, I'll discuss the future possibilities. Artificial neural networks is a mathematical algorithm to fit nonlinear and complex models. When they are trained with sufficiently large data sets, they can outperform human brains in some cases. As such, they are widely used in industry and research, such as for image recognition, speech translation, and decision making. The mathematical model of artificial neural networks includes the model of the network and the model of the neuron. For the network, it contains an input layer, several hidden layers, and an output layer. For the neurons, each neuron has multiple input nodes connected together by synapses and an activation function to scale the summed output. The network parallelism, which is the scale of the network, can directly determine how intelligent the network is. So to enhance the capability of the network to processing even more complex tasks, the network's parallelism need to be enhanced. While each neuron's matrix multiplication or nonlinear operations directly determines the computing speed of the whole hardware. So to enhance or accelerate the operation of artificial neural networks, the matrix operations needs to be accelerated. In terms of research on artificial neural networks, some people work on algorithm, while some work on hardware. And as for hardware, there are typically two kinds of architectures. One is the digital, another is the analog. So the main difference between them is whether the von Neumann architecture is employed, in which the memory and the processor are separated, which means that if you want to process or calculate something, you need to read the data from the memory and compute the processor, then write the answer or the result back to the memory. This kind of architecture has an obvious advantage. That is, if the memory is very large, then you can basically demonstrate matrix multiplication of very large dimensions. However, the main drawback of this architecture is that you need to write and read data back and forth from the memory to the processor. So a lot of energy is wasted and a lot of computing power is wasted. In terms of analog architectures, there are electronics and optics. And of course, the electronics are the mainstream technology that is mature fabrication techniques and the high integration density. However, there is the so-called electronic bandwidth bottleneck that limit the processing bandwidth of electronics to around 1 gigahertz. While in contrast, their optical counterparts can provide ultra-wide bandwidth of over 30 terahertz. So in the future, I believe that hybrid optoelectronic neural networks that can leverage the advantages of optics and electronics will be developed. Such kind of hybrid architecture could enable a computing speed much higher than pure electronics without sacrificing the flexibility of electronics. This is some milestone works that I've collected. Of course, it's not comprehensive, but they can review the development in terms of the optical neural networks research. First, people realized that using optical loops via the low loss characteristics of optical fiber, thousands of temporal nodes can be achieved. And after mixing them in a laser, reservoir computing can be achieved. And later, wavelength division multiplexing was introduced to achieve a vector computing. And later, 4 years later, an integrated chip was developed, which first shows that these optical neural networks can be fully demonstrated on a single chip. And this means that optical neural networks has the potential to partially replace their electrical counterparts. And 1 year later, diffractive lens was employed to achieve large-scale synapses of optical neural networks. And just 1 year later, on-chip memory was achieved to realize a spiking neural network. And at the same year, a review paper was published. And this year, over 8 Nature Family papers are published. So this is definitely a hot topic. There are 2 reviews on Nature and Nature Photonics, and 2 back-to-back papers on Nature, a paper on Nature Photonics, and the 3 other Nature Family journals. So For the existing works, there are the integrated MCI arrays we've talked about in the reservoir computing, diffractive optics and phase-changing materials, and all of them has solved or offered a puzzle of optical neural networks towards the final application for real-life tasks. However, all of these previous works are demonstrating fully connected neural networks. And they are subject to two major common limitations. One limitation is the low computing speed, lower than 20 gigaops per second. Another limitation is the limited fan-in due to the fully connected structure, because in such analog optical structures, the number of input nodes is directly determined by the number of physical connections and synapses that you realized. So it's quite limited. So this brought us to a question: how can we achieve high computing speed that is promised by the broad bandwidth of optics, and also with the sufficient fan-in for real-life data that thousands of millions of data points are processed for a single computation. So our solution is convolutional neural networks. So we use convolution operations to extract hierarchical features to greatly reduce the parametric complexity of the whole network, such that very large data sets can be processed with a small and simple network. However, we know that right here, the computing cost is not reduced. So the convolutional neural networks still needs to be accelerated, especially the convolution operations that can take over 85% of the total computing power cost. So this is our paper that was published early this year. We are lucky that our paper was highlighted on the front page of Nature website for 1 week, and it was the only research work. So this is the overall structure. It includes the multi-wavelength source, modulator, dispersion medium, and photodetector. The kernel size of convolutional neural networks is generally very small. It's generally 3 by 3. It's definitely within the capability of analog optics. And the input data is fed into the modulator as in the forms of temporal waveforms. So it can be indefinitely large in theory, provided the ADCs or the DACs or memory are sufficiently large. So the duplicated signals of all wavelength channels are useful, as you can see from the color box right here. So the computing speed is the number of wavelengths times the modulation speed. So this slide shows a more detailed explanation of the process. So the weight vector, which is the kernel's weights, convolutional kernel's weights, are mapped onto the optical power of all the wavelength channels, while the input data X is mapped onto the intensity of a temporal waveform. So the input waveform X is broadcasted onto all the wavelength channels and weighted simultaneously by electro-optical modulation. And then the multi-channel signals are passed through a dispersive medium, such that the signal at different wavelength channels are progressively delayed. And finally, they are summed upon photodetection. As you can see, at different time slots, the output waveform, the output results at different time slots corresponds to the dot product of the input signals, of the input data within a certain window, and the weight vector. As such, we essentially achieved a sliding convolutional window at the speed of the modulation rate. The vector computing speed. So this performs a vector convolution between the input data X and the weight vector W. So this vector convolution computing speed is 2 times n times p, where n is the total number of wavelengths. Right here is 4, and p is the symbol baud rate of X. So right here we shows that how a vector convolver can be achieved, and right here we show how it can be used for matrix convolution. So the main process is that the input data and the convolutional kernel matrices needs to be flattened into vectors in some specific orders and follow some rules. So as you can see from this image, within the green box, the data are multiplied together and summed. As you can see, by performing the convolution between these flattened vectors, the convolution between the 2 matrices can be achieved. Right here, you will notice that the output Y, they are sampled to construct the convolved feature map, and some of the time slots are unused. So this would cause a overhead in the speed in terms of computing matrices, which we'll talk about later. So this is the result of our microcom generation. So we used a novel architecture or a novel scheme of solid microcoms, which is the solid and gray cells. So different from the single solid state, solid and gray cells has many solid circulating in the ring cavity, which means that the intracavity power is much higher than a single solid state. So when you change the detuning between the pump wavelength and the resonance to reach the coherent state, because of the high intracavity power of solid and gray cell states, the resonance won't be pushed to the below side if when you switch from the chaotic state to the coherent state. And as such, such coherent microcoms can be even generated manually by manually tuning the pump laser. So the coherent states can be dialed up on command without the need of complex feedback control of the pump laser or the resonance. And over 90 com lines are generated in the C-band with an FSR of 50 gigahertz. So this shows our result for processing a human being face image. We achieved 10 kernels, 10 3x3 kernels, and the input data rate of this image is at 62.9 gigabaud. We used 90 commas in total, 9 for each kernel. The data input scale reaches 250,000 pixels, which is very large in contrast to prior arts. The vector computing speed reaches 11 teraops per second, and the matrix computing speed is 3.7 teraops per second. So this is because of the overhead that we've talked about. The overhead is directly determined by the kernel's height, because right here we use 3x3 kernel, which means the height is 3. So the matrix computing speed would be 1/3 of the vector computing speed. Then we used the convolutional accelerator to demonstrate a convolutional neural network. We used it to demonstrate the convolutional layer, and reconfigure it to demonstrate the fully connect layer. While for the nonlinear activation functions and the pooling functions, we demonstrate the electrically. This shows the data set, the handwritten digit images, and the corresponding high-speed waveforms that we've demonstrated. We experimentally tested 500 images due to the limit of the memory of our AWG. We split the data into 10 batches, each containing 50 images. We multiplex them as high-speed temporal waveforms. So for the convolutional layer, we use 75 fluence channels in total, which corresponds to 3 5x5 convolutional kernels, and the convolutional stride is 1x5. So for each convolutional kernel, they would yield a feature map, 3 feature maps, thus three feature maps with a scale of 6x26 are generated. So this image shows shows the feature maps, experimentally generated feature maps of the convolutional neural network. So the feature maps are further pooled to a smaller size, which means that the 3 feature maps can be converted into a vector with a length of 72, which is the input vector of the following fully connected layer. So in the fully connected layer, we have 10 output neurons, each with 72 synapses. And thus 72 wavelength channels are employed. The input feature maps of 50 images are split into 2 batches because the dimensions are much smaller, so we can finish the processing with just 2 batches. This is the result of the fully connected layer. You can see at different neurons, they can provide a predicted intensity for each image. Batch 1 and then batch 2. So this is the result for 50 images. You can say that for each image, all the neurons will output an intensity. So the neuron that has the largest intensity would indicate the predictions for the image. And this matrix is the confusion matrix that shows the predicted results. Ideally, if the accuracy is 100%, then the numbers should all be on this down the line. However, there are some errors. The main error is the theoretical limitation, because we only used a single layer in the fully connected part for prediction. And in our calculation, if we use 2 layers, the accuracy would rise to over 96%. This is the result of the full 500 images. You can say that the experimental results and the calculated results matches very well in terms of the distribution of the neurons' output intensity. Finally, I would like to acknowledge my collaborators from Swinburne, Monash, RMIT, IRS, City University of Hong Kong, and the CAS. I'd like to also mention that I'm going to join Beijing University with Post and Telecommunications soon, so we have positions available. Please contact me if you are interested. Thank you very much.
So thanks to Mike for his introduction on optical neural network, in general artificial neural networks, and for presenting his work on convolutional neural network implemented on photonic integrated circuits and achieving 11 tera operations per second. If you have any questions for Mike, please feel free to contact him in the email that he left on the slides, or just look up for him. And this was the last talk of the sessions. I like to thank really once again all the speakers of the session and also everyone who joined and participate in this first session of our conference. Now we will have a break and we will be back at 11:45 with the second session, which is Advanced Optical Materials. I also would like to remind everyone that we have a poster session going on, and during the break I really encourage you to just go and have a look to all the posters that have been submitted, and you can do so by following the link following the QR code that will be posted in the slide that is going to be online just after me, or you can just follow Wiley WeChat account, or just to refer to the link that you can see in the live chat here in the conference. So thank you very much for everyone who joined, and I will see you later in roughly half an hour. Bye-bye.
So good morning, everyone. My name is Yinan Zhang, and I'm an associate professor of the Institute of Photonics Chip in the University of Shanghai for Science and Technology. I'd like to welcome everyone to the Advanced Optical Material session. This section will focus on mathematics and meta-surface, optoelectronic neuromorphic devices, and multifunction nanomaterials. I will briefly introduce every speaker before giving them the floor. The speaker will have 15 minutes for presentations, and I will notify them if the time limit is exceeded. At the end of each talk, there will be a question and answer session. The audience has the opportunity to ask questions to speakers. I'd like to remind everyone to please mute your microphone if you are not presenting. For this session, the plenary talk will be delivered at the end of this session due to the time zone of the plenary speaker. So now let's start with the first speaker of the session. The first speaker of this section is Professor Dragomir Nashev. Professor Dragomir Nashev is Professor of Physics at the Australian National University and Director of the Transformative Math Optical System Center of Excellence in Australia. He has worked in the field of optics in several research centers around the world and joined the Australian National University in 2002. He has received multiple awards, including the Queen Elizabeth II Award in 2010, the Australia Research Award in 2004, the Marie Curie Personal Award in 2001, and the Best Young Scientist Academic Award in 1999. His research field involves several branches of optics, including periodic, photonic structures, singular optics, plasmonics, and optical metal surface. I will now give the floor to Professor Nashev. Professor Nashev, can you start if you're ready?
Thank you, Ian. Can you just can you hear me well? And can you see my slides?
Yes, we can see the slide.
Okay, awesome. Thank you so much, and thank you so much for the introduction. So the title of my talk today will be on the electric meta-surfaces for nonlinear and quantum light sources. And I am, as you mentioned, from the ARC Center of Excellence for Transformative Meta-Optical Systems, which is a center that we started together with Professor Minggu when he was still in Australia, and now first year of our center. So before I go to the real research, I want to thank all my collaborators that contributed to this research, which I will present today, from the Australian National University, from Nottingham Training University in UK, from University of Brescia in Italy, and from the University of UNSW in Canberra in Australia. Because, as you mentioned, our plenary talk will be the end, I want to just start with a very quick introduction about optical meta-surfaces, which are sub-wavelength arrays of nanoscale optical elements, which are placed on a surface, and importantly, the wavelength of light is much larger than the periodicity of the meta-surface, so the light fills this surface as a homogeneous material. And you see here two examples of plasmonics and the electric meta-surfaces, and I will focus mostly on the electric materials, where we have a very strong light confinement inside the resonators due to resonances that are excited, and because of the resonances, the light that is re-emitted from the resonances is re-emitted with defined phase, polarization, and color, which will be the topic of this talk. When we speak about resonances in metasurfaces, that in the electric metasurfaces, there are two main types of resonances. The ones that is most studied are the so-called Mie resonances, that are localized resonances due to excitations of displacement currents inside the electric nanoresonators that are placed together for the metasurface. And there are two type, electric and magnetic type families, and that's been observed in a number of works so far. More recently, a high quality factor resonances, which exist due to lattice excitation of lattice resonances inside such periodic structures, have placed a big attention. And these are the so-called bound state in the continuum resonances, which are excitation of modes above the light line, but because of the even symmetry of these modes, they cannot radiate in free space. And because of this, they effectively have a very high quality factor that can be excited. And these are the resonances that we will explore in our case. And because of these resonances, we have a very strong enhancement of the electric field inside the material. And this strong enhancement gives rise to strong nonlinear effects, which are due to the high electric fields that drives the electrons of the materials beyond the harmonic oscillations. And what does this mean for metasurfaces? The fact that we have several resonances which can be at all of the waves that are participating inside the interactions inside the metasurfaces, we have significant enhancement of the nonlinear polarization, which is the polarization for generation of these third waves at omega 3, which is at much larger, a much higher energy. And the enhancement is proportional to overlap integral between all these three modes that exist in the metasurface, the electric susceptibility, the second order electric susceptibility of the material, and importantly, multiplication of the quality factors at each of the participating wavelengths. So as I mentioned before, if we can excite quality factors, and these are quite moderate quality factors that can be readily excited in metasurfaces today, between 10 and 100, but one can think even 10,000 or more can be excited, have been observed. For such moderate quality factors, we can make a comparison that a thin metasurface, just a few hundred of nanometers, can behave or can convert light as efficiently as a thick nonlinear crystal of 1 millimeter thickness. This is what we have mostly in our lasers, what we use in the lab. But at the same time, for metasurfaces, we can do this on a flexible substrate. We can do a lot cheaper because of the lot smaller amount of the material that it's required. So why is this important? This is important because practically we can replace all of our nonlinear materials with the ultra thin layers based on metasurfaces. And this has driven the field, starting already with plasmonic metasurfaces and most recently the electric metasurfaces with cubic and quadratic type nonlinearities. However, what is very important to mention is that despite metasurfaces being homogeneous materials for the fundamental wave, which is defined by the so-called non-diffracting condition, that means the periodicity has to be smaller than the wavelength divided by the refractive index of the surrounding material, which effectively gives us this propagation of the light unchanged to the material. We have to think that this condition actually is not really preserved for the harmonic waves. For example, for the second harmonic wave, in this type of second harmonic interaction, for a typical metasurface of 750 nanometers made out of aluminum gallium arsenide, what we will see a bit later, for this metasurface, the actual emission of the harmonic waves is no longer homogeneous. Metasurface in this regime is diffracting metasurface, so the light is actually not going as a crystal, which is our big dream, but it's actually transferred into diffraction orders. So the metasurfaces are always diffracting at the harmonic waves, at least what we've seen today. And this is one example showing the back focal plane image of an emitted second harmonic from aluminum gallium arsenide metasurface. And you see here these four orders. The light is emitted into four diffraction orders, and very little light is actually going along the center of the material. So the question is, if we are talking of metasurfaces as good nonlinear light sources, can we actually make a metasurface that can emit in a single order? And what do we need for this? And the simple reasons are that you need a material with very high refractive index, so you can make a very small resonators out of this material, and you can pack these resonators very densely, so this periodicity or non-diffracting condition is fulfilled for all waves. And to do this, we thought, what is the highest refractive index of naturally existing materials today? And so far, people have been using 3-5 semiconductors, silicon, but in fact, transition metal dichrocogenide have extremely high refractive index. Refractive index more than 4, with nearly zero absorption in the wavelength range above 720. This is particularly for MOS2 material. So we thought, can we actually use this material and can we make a metal surface that is nonlinear and is not diffracting for any of the fundamental waves? Not just for the fundamental waves, but also for the harmonic waves, second and third harmonic. And indeed, such resonators have been shown to exist, sub-wavelength resonators made of TMDC materials. This is WS2 materials. However, this is less transparent in the visible spectral range. So we thought, can we actually fabricate something from MOS2 and study its nonlinear properties? And we did this by transferring a thicker layer, about 150 nanometers layer, on a glass substrate, and nanostructuring this material using electron beam lithography and refractive ion etching. By doing this, because of the high refractive index, we could pack very close density this material, these resonators, and have a periodicity only of 300 nanometers. And for fundamental wave of 1515, we have lambda over 5 excitation here of the so clearly preserving the non-diffracting condition even in the presence of substrate of 1.5 refractive index. However, to be absolutely honest, this condition could not be fully fulfilled if we have all the resonances at the fundamental waves. So we had to shift actually the resonances to be at the second harmonic waves. And we see here the magnetic dipole resonances are here in the range of 800 to 700 nanometers. And we study the nonlinear properties of such metasurfaces, which is fully homogeneous for the second and third harmonic waves. And we saw first surprise. So when we studied the second harmonic enhancement, we expected this will be the case that we will have strong resonance. Every resonance will be enhanced by the quality factor. But we saw that actually the strong enhancement happens at the magnetic quadrupole resonance, which it happens because of twofold. The first one, because this is near the band gap of this material. So we have a strong near band gap enhancement. But secondly, the symmetry of the mode of this magnetic quadrupole is completely different than the symmetry of the mode of the electric dipole. And we have this opposite current at the top and the bottom surface. So in order to then fulfill this very strong enhancement of the material, there was only one choice, that the sources of the nonlinearity actually in MOS2 happen not from the bulk of the material, but only from the bottom and from the top layer that is excited. And the interference between top and bottom layer give rise to very exciting new phenomena. But first, indeed to prove that this is second harmonic emitted from the top and bottom layer, we also run a polarization dependence for the copolarized light, and we see this butterfly type, typical butterfly effect, which is modified a bit of the resonances. So these two lobes are slightly suppressed due to the presence of the electric dipole resonance. And the new physics that we saw is that by controlling the wavelength, the polarization of the incident light, we can direct this light that is going in a single beam, we can direct it either completely in the forward direction. So if the polarization is here around 15 degrees from the normal, from X coordinate, or in backward direction by turning around 70 degrees of the initial polarization in plane. And obviously by changing the polarization, we can switch this emission between forward and backward direction in completely controlled fashion. And this is happened because not just because of the polarization, but also because if we tune the wavelength across the resonances that we are exciting. So this was a completely unique type of nonlinear source that does not exist even in any type of other nonlinear materials, which source that can be directly, controllably directed in forward and backward direction. So this was very exciting, but of course, for any field, in order to have any drive, this field has to have good applications. And one of the applications that we saw for such nonlinear light sources was to generate entangled quantum light. First, what we did was, so an entanglement is generated by a process called spontaneous parametric down conversion, which happens when one photon is being split into two separate photons with the conservation of the energy of the momentum. And this is one well-known effect for bulk crystals, where these newly generated photons can be emitted at different wavelengths and in different directions. And if we have nanoscale light sources of such entangled photon, you can imagine we can pack up a lot closely density on chip of such sources, and we can drive new applications for communications, imaging, and sensing in quantum light sensing. So the first experiment that we did was to create aluminum gallium arsenide nanoresonators, excite these with a wavelength of about 780 nanometers, and look at the emission, spontaneous emission of signal Nadler photons out of these waves. So we collected this with a very large numerical aperture objective. So we collected all the photons that are emitted, and we put these through a beam splitter on two single photon detectors. So the emission is around, in the telecom, around 1550 nanometers, and we counted the coincidences of these photons. And what we saw is, first we see some background, broad background due to the emission, just a thermal emission from such resonators, but we also saw a strong emission of SPDC photons, which is about 2 sigma for our generation, for our experiments. And this is an experiment that was going over 24 hours to count all these coincidences. So the total rate was 34 Hertz. So it was a heroic experiment, but we managed to demonstrate for the first time these coincidences. But of course, for this type of quantum light to be any useful, one would need to have really much higher intensity, much higher rates of emission. And for this, we employed now a BIC type, Bernstein continuum type resonances, and not just one, but actually 2 of them, in order to create this hyperbolic dispersion. And with this, we were able to enhance the emission over 5 orders of magnitude with respect to an unpatterned film, 3 orders of magnitude with respect to the me-type case, which we said before, and 2 orders of magnitude if we just have a single BAC type resonance. And these photons could be entangled, and this entanglement, which is shown in these bright spots here, for depending on the pump polarization and the emission angle. So the entanglement can be seen also when you detect a particular azimuthal angle of emission for a particular input polarization. But this type of entanglement really shows the great possibility for such light sources for quantum type application, particularly generating design bandwidth, angular distribution, and entanglement. And with this, I go to my conclusion. Nonlinear metasurfaces is a really promising platform for nonlinear and quantum light sources, but still a lot of research is needed to mature the platforms and applications of these metasurfaces. So thank you so much for your attention.
Okay, thank you very much, Professor Nashev, for this great talk on the dielectric metasurface for nonlinear and quantum light sources. And now we can open the question and answer session. So the first question is regarding the BIC. So at the beginning of the talk, you mentioned that BICs can achieve very high quality factors and described that BIC with a quality factor in the order of 10 to 100 are cheap and easy to fabricate. So what is the practical difficulty for achieving high Q factors?
So, okay, I come here to this talk. So the practical difference for achieving high Q factors are effectively the losses in the material. So still there is always some residual loss when you use silicon or gallium arsenide. And also the fabrication imperfections so you need a very high quality of the fabrications. So typically what people can achieve is between 100 and 1000 Q, and 10,000 Q, as far as I know, is from Jin Liu from Sun Yat-sen universities. But I think with the maturing of these technologies, we will we're seeing more of these 10,000 type quality factors. In our lab, we have the best we have managed, actually, I have to be honest, is about 1,000.
Yeah, okay, thank you very much. And the second question is regarding the MOS2 up conversion. So you talked to the MOS2 is very high index and low loss in the near infrared range. So how about the stability of this material?
So MOS2 actually is quite stable in ambient environment, in air, and we have done these experiments over more than a year, what it took us. So we actually went back and forth even with the reviewers to repeat some of the experiments, and the samples were absolutely stable. So we don't see any degradation, especially that these are thicker type materials. So if any kind of changes that happens maybe on the side surfaces that maybe have some dangling bonds there, but top and bottoms, so everything is very, very stable.
Okay, thank you very much. And so due to the time issues, we have to move to the next speaker. And let's thank Professor Nashiv again for your wonderful talk and answering the questions. So our next speaker is...
Thank you so much for having me.
Thank you. Our next speaker is Professor Zhou Ye from Shenzhen University. So Professor Zhou Ye is a fellow of the Royal Society of Chemistry and works in the Advanced Research Institute of Shenzhen University. His research interests include flexible and printed electronics, nanocomposites, and nanoscale devices for logic circuits, memory, photonics, and sensors. He has published in Science Chemical Reviews, Nature Electronics, and Nature Communications. He is also a journal editor or member of the editor board of Material Horizons, Multifunction Material, the Vacuum, and other journals. So I will give the floor to Professor Zhou. Professor Zhou, can you please share? Yeah, okay. So Professor Zhou, can you start if you're ready?
Okay, thanks for the introduction from Professor Zhang, and great thanks to USST and Wiley to organize this great event. So it's my pleasure to present our recent work on optoelectronic neuromorphic devices for functional applications. So today my talk will, I will first briefly introduce the memory, the background of memories, and I will talk about our recent research work. So for the memory, we can have mainly two characterized. One is called the volatile, and another one is called the non-volatile. So for volatile, we have the very good commercial product. For example, the static random access memory or the dynamic random access memory. And for non-volatile, we have the main product called flash memory. And also we have a lot of emerging technologies. For example, the MRAM, PCM, RM, and so on. So for SRAM and DRAM, so that is volatile. Why we say it is volatile? Because these data can only be stored in this kind of a device for quite a short time. But if you maintain the power, then these data can be maintained. So for the market, so mainly we have the flash memory. And for the flash memory, we can have the NAND type or the NOR type. And for the DRAM, we are keeping decreasing the size of this kind of the technology. So the main show is the flash and DRAM, but these are the complementary technologies, because for the flash, it has low speed, but the data is non-volatile, and for the DRAM, it has a high speed, but the data is volatile. So in the memory market, or in this kind of the technology, we need to keep increase the data storage density. So mainly we have two ways. One is to reduce the device size, and another one is we can have something called the vertical multi-layer structure. So then we can not only to fabricate the device on the 2D plane, but we can stack the device and to have the high density of the memory cell. So mainly the Korean manufacturer dominates the DRAM and flash market, as you can see in this picture. But when we keep reducing the device size, there's some problems. For example, the quantum uncertainty or the cost to keep reducing the size of the device. And when we reduce the size of the device, we will cause a lot of leakage. and the high current will cause a heating problem. So we are saying that the Moore's law may gradually fail. So in the industrial guy may say we can have many choices. For example, we can follow the more or more than more. So that is to use for example, the new mechanisms or new processes, architectures, or paradigms. So then we can increase the speed of these devices or the density of these devices. And this figure shows you the development of the memory. So start from the 1947, we have the first RAM, and then we can go to the read-only memory, and then the SRAM and DRAM, and the EPROM is the precursor of the flash memory. And finally, in 1988 and 1989, we have the two mainstream of flash memory, which is called the NOR and the NAND. And after even more than 20 years, and in 2015, the Intel and Micron, they advised the new type of the memory. So that is a kind of the two-terminal memory. And this breakthrough says that it is 1,000 faster than the NAND flash, and it has 1,000 times the endurance of the NAND flash, and even it is more denser. So for the memory device, we need to consider, and we focus on the different performance of the memory. For example, the storage density, how many data can we store in these memory cells, and the retention time, how long we can store the data. And of course, the read speed and the write speed is very important, since we need to put a lot of data in the memory cell, and also the endurance and yield. So the yield is very important in the production line. So for the two-terminal memory, actually, we have a lot of choices, not only for the Intel and Micron, they say that is a PCM. And also we have other choices depending on the different mechanism. So for example, if we talk about the filament control or some interface control, we can fabricate the resistive random access memory that is based on the resistance change of this two-terminal device, and also the phase change memory. So that is a phase change from the non-crystalline to crystalline material. And also we can use some magnetic material or the ferroelectric material to make a magnetic tunnel junction, or the ferroelectric material to make the FRAM. So these kind of the devices, these are two-terminal memory, so they can be very dense, actually several times of the DRAM, since the DRAM is one transistor with one capacitor. So if we use the two-terminal technology, then the area of the single memory cell can be further reduced. So my research is mainly focused on the RM, or sometimes we call it is memories. So this kind of the device, when we tune the electrical conductive states of the device, we can have the different type. For example, we can have the analog type, that is a gradual increase of the conductive state, or we can have the digital type. So that is a very high rupture of the filament. Then we can have the binary memory state. And even for these digital type, we can have the volatile or non-volatile. So to conclude, the advantage of this kind of the memories or RM, so it has a high speed, and the power consumption is very low, and can achieve a very high endurance and the scalability due to the two-terminal architecture. And if we use a CMOS compatible material, so then we can easily integrate this kind of a device with the CMOS circuit. So in this area, we need to find the proper material to behave the resistive switching behavior, and identify the physical mechanism under the resistive switching, and to solve the problem. For example, the endurance, the stability, and the data retention, and to achieve the effective regulation. So this kind of the technology can partially solve the problem. As I mentioned, we need to increase the density of the memory cell. But actually in the computing architecture, we have the bottleneck, which is called the von Neumann bottleneck, because the CPU, the central processing unit, is separated with the memory. So we need the bus to do the data transfer. So this picture is von Neumann with the first electrical computer, the ENIAC. So then if we have a lot of data transfer between the CPU and the memory, it will cause a lot of problem. For example, the power consumption. So this power consumption will make the memory will become the main bottleneck of our advanced information system, because the performance difference between the CPU and the memory will cause a memory war. And also this kind of the architecture, so that is a separation of the CPU and the memory. Actually, that is very difficult to meet the increasing demand for the energy efficient and the speed of today's technology. So what we do is the scientists and will can bring some ideas, for example, the brain-like computing or the brain-like memory. So the human brain is actually a very superhuge parallel computing system. It has a lot of neurons and synapses, and we can learn from the efficient working principle of the brain. So because that is a parallel system, so we can keep reducing the data movement. For example, we put closer of the controller and the control unit with the memory. So we start from the near memory computing, then we can go to the in-memory computing. So this is one development trend for the brain-like memory or brain-like computing. And also in the structure, we can more mimic the neuron and synapse and to form the neural network. So we can build the artificial neuron or artificial synapse. And this kind of the large neural network can have the advantage over the traditional computing system, over the von Neumann system, because it can process the intuitive information or these unstructured information more efficiently. So the memories actually can be used in this area, and also it can do a lot of things compared with traditional CMOS technology. So the memories can do the logic operation or the matrix vector multiplication, or even it can go for some physical unclonable function, the path or the trinomial number generation. And of course, if we make the neuron or the synapse, we can build the neural network. So that is spiking neural. If we organize more devices into this neural network, we can build something called the artificial nerve. So that is the integration of sense, memory, and computing. So our research will mainly focus on the composite material, and we are caring about the optoelectronic coupling, since it can tune the memory or the logic computing. And of course, these optoelectronic coupling can sense and process the information. So the one work we have done is to use the light to control the logic operation. So the memory is a two-terminal device. We can use electricity to switch the memory state from the low state to the off state. But actually, if we use this optoelectronic sensitive material in the memories, then the light can also control another kind of the memory state. So if we have these different states and we use the light or the electricity as input, actually we can design these light controlled logic operation to use the light or the electric field to control the computing. So this is one kind of the demonstration. And also the light can control the set voltage of the memories. So actually for the logic computation, if we use memories to build this circuit, the set voltage is very important. So in this circuit design, if we can use the light to control the set voltage, as you see in the figure, if we use a different light from the blue light to the red light, then we can really control the set voltage in a very large range. So this kind of the performance can help us to do a reconfigurable computing, since if the set can also control the volatile property of the device. So usually the memories. So they are non-volatile if we use these nanoparticles or quantum dots to fabricate the device. But if we use the UV light to excite the device for a long time, then this kind of device, under the excitation of the UV light, it can transfer from the non-volatile state to the volatile electrical switching. So that is called the threshold switching. So if we have the threshold switching, actually we can do a lot of things. For example, we can build the array and for the memory state storage, or we can build this RC circuit to mimic the neuron. So that is the artificial neuron which we can derive from the memories. And also, even we can connect the memories array with the source cell. So the source cell can sense the different ways of the light and transfer the photon energy to the electrical output. And these electrical excitation actually can tune the memory state of our memories. So we fabricate the memories, and also we seriously connected this memories array with the source cell. And this source cell array can sense the irradiation intensity. And also, it can sense the irradiation wavelengths. So it can help us to do the noise reduction of the input signal, and also can enhance the contrast of the input signal. So that is a simple demonstration of the memories. So to conclude, we have focused on the ion transports of the organic, inorganic composite devices, and also the charge transport, including the electron and hole. And the ion dynamics and carrier dynamics is very important since it can reveal the mechanism of optoelectronic synergistic enhancement, and also it can expand our application. For example, we are more focusing on the brain-like computing or brain-like memory. So finally, I want to acknowledge the fundings from the different organizations, and also special thanks to my hardworking students and postdocs. Without them, we cannot achieve these results. So this is the end of my talk, and thanks very much.
Okay, so thanks, Professor Zhou, for your interesting talk on the neuromorphic devices, particularly the memory register. And now we can open the question and answer session. So the first question is, what is the state-of-the-art density of memory structures?
So you mean the state of the, so which kind of the memory? You mean the memories?
I think this is like a general question regarding the memory. Well, what is the state-of-the-art, the density?
Oh, the art of density things actually. For the memory, we, as I say, this mainstream memory technology is still the flash memory and the DRAM. Actually, we are keeping reducing the size of these devices to have the high density. But in another way, we have a lot of advanced technology. As I say in these slides, we have the PC RAM and also the MRAM or the RAM. These kind of the technology can replace some part of the mainstream memory technology and help us to have high density or even portable devices to use this kind of the technology. So we are trying to find more suitable structures and technologies to help us to remember the information more permanently, or we can have more functions to do these brain-like memory or computing, such kind of these things.
All right, thank you. So the second question is regarding the memory register array. So you talk about the memory register arrays, and in your work, what is the feature size of the single memory register, and how do you fabricate the array?
Okay, the single size of our memories, that is depending on the material we select, and the common size should be the several tens of the micrometer for the two-dimensional devices. And when we fabricate these devices, because most of the material are organic, inorganic materials, so we first fabricate one layer of the electrons and spin coating, or do some physical deposition method to fabricate the active layer. And finally, we use thermal evaporation with the shadow mask to fabricate these devices. So these devices actually are not small enough. The size is in the several tens of the micrometer or even several hundreds of micrometer. So if you want to reduce the size of the devices, we can use the photolithography the method to do that.
All right, thank you. So in your work, what is the minimum size you can achieve? Can be like a few micrometer?
Yeah, the minimum devices we fabricate in our lab is a few micrometer. Even we can go to the 1 micrometer. And also we have tried some method with the E-beam lithography. Then we can go to the several hundreds or even several tens of nanometer.
Okay, thank you very much. So we probably need to move to the next speaker, and thanks Professor Zhou for your talk and for your effort answering the questions.
Okay, thank you very much.
Yeah, thank you. So our next speaker is Professor Xi Chen from USSG. So Professor Xi Chen is a professor of the Institute of Photonic Chips of USSG. He received a doctorate from Nankai University in 2006 and a doctorate from Queensland University of Technology in 2010. After that, he worked in Swinburne and MIT in Melbourne. Professor Chen's research focuses on artificial intelligence, nanophotonic materials, and related renewable energy fields with the purpose to develop the advanced artificial intelligence technology through material innovation to achieve a smarter, greener, and safer future. So let's welcome Professor Chen. Professor Chen, can you start if you're ready?
Okay, so thanks, Ina. So can you see the slide?
Yes, we can see.
Okay, so hello everyone. So this is Xi Chen. So I'm a professor in the Institute of Photonic Chips, University of Shanghai for Science and Technology. So today is my great pleasure to make a presentation here. So the topic is about the integratable diffractive deep neural networks. So I have listed my email address in the slide. So if any questions, please feel free to send emails to me. Yeah. So the first, I would like to introduce our institute. So it was launched in January 2021. So led by Professor Minggu. So it's a multidisciplinary institute, including optics, optical engineering, material science, computer science, and biology. So now the institute has more than 30 academic staff members. So all of them are PhD holders from the top domestic or overseas universities. So now we have established the world-class facilities, 2,000 square meters, including the optical labs, the material labs, the biomedical labs, and the clean room. So the research aim of our institute is to develop the cutting-edge AI photonic technologies to make a more intelligent and greener future. So why the AI can link with the photonics, and why this kind of link can turn the human being's future better? So now, the AI is a quite hot topic. Everyone can talk about the AI. So actually, one of the landmark events was in the 2016. At that time, the AlphaGo beat the world champion Li Shishi in a 5-game match. So the win has chosen by the Science Journal as one of the breakthrough of that year. So although current the AI technology seems strong enough, so the future is still the questionable, because we cannot find an innovative pathway to realize such the AI technology. So think about it. If we have looked at the energy consumption behind the AlphaGo and behind a human being. So the AlphaGo contains several hundred CPU and GPUs. So the total energy consumption is around the 1.25 million watt. But a person only takes the 20 watt. So it means that the 60,000 people the energy conduct a single task and just beat one people who can do multiple tasks. So we can imagine if we use the current electrical-based pathway to make a multi-task brain-like system. So this kind of energy consumption of the brain-like system is definitely not acceptable by the modern society. So if we enable the AI by the photonics, so we can take the advantage of the photonics, such as the low energy consumption, is 1,000,000 times less than the electrical pathway, and also take the advantage of the highest speed and the multiplexing through the intensity, through the wavelengths, through the polarization. So in this case, so we can claim that the AI combined with the photonics can provide a pathway to solve the bottleneck issues of the current electrical-based AI technology and bring a potential to realize a green future. So in the development of the AI photonics, milestone achievement is the so-called the diffractive deep neural networks, so D2N. So this outcome was announced in Science in 2018. So it can implement the classification of the handwriting digit images through an all-optical deep learning framework. So the input is the coherent light source, the laser, and the framework itself conformed by the 3D printed multiple layers of the diffractive surfaces. So each point on the layer either transmits or reflects the incoming wave. So it can be considered as the artificial neuron. So the neurons on one layer, it can be connected to each other through the optical diffraction, and each point on the layer can act as a secondary source of a wave. So the amplitude and the phase are determined by the product of the input wave and the complex valued transmissions or reflection coefficient at that point. So the design is made by the computer algorithm. Through this kind of the input interference pattern and this kind of local transmission and reflection coefficients, so we can consider each point or neuron can have various term. So actually this is the learnable network parameter. And this kind of parameter can be adjusted during the training process. So using an error propagation method. After the training phase, so the D2N design can be fixed, and the transmission or the reflection coefficients of all the neurons are determined. So the digit classification outcome can be observed at the output layer with the intensity profiles. For example, when we input 1, so the highest intensity is at the first absorption area at the output layer. So 2 at the second area, 3 at the third area. So in this case, we can claim the D2N can classify the digits. So here is the experimental setup of the D2N. So it's the terahertz setup. So we can find that the optifier and the multifier chain was used to generate the continuous wave irradiation at the 0.4 terahertz, and the mixer optifier and the multifier chain was used for the detection at the output plane. So using this kind of setup, so the phase only the D2N can reach the recognition accuracy around the 81%. So by increased number of the diffractive layers to 10, so in this case, the total number of neurons could be the 0.4 millions. So the accuracy can increase to the around nearly the 87%. So if we compare with the electrical pathway, do this the same task using the convolutional neural network. So the state-of-the-art performance could be the 97, but through the electrical pathway, they use the neuron, the number is around the 2.5 million, but for the optical wave, it's only the 0.4 million neurons. So here show the performances of the handwriting digit classification. So a 3D printed D2N can successfully classify the handwriting input digits from 0 to 9, so totally 10 numbers. So the result showing under the 10 different detected regions. So actually, the red dashed area, we can find that each link to 1 digit. So we can find that the output image for the handwriting input of 5 can be shown. And the figure B is the confusion matrix and the integer distribution percentage of the experimental results. So here they use 50 different handwriting digits, 5 for each digit for the training. So we can find that the training was successful. Then they increase the handwriting digits to 10,000, and finally get the accuracy is nearly 92% for the 5-layer design. If they increase the layer number to 7 from 5 to 7, so the increase can further increase to the 93%. Okay, so actually the sun paper is first the result of the D2N. So after that, many research groups jump into the area. So next I will introduce some outcomes of the D2N development. So in the sun paper, only the 0.4 terahertz can be used, but later some work aims to expand the working wavelength range. So the Chen's paper published this year, they use the broadband terahertz source from the 200 to the 420 GHz, so as the input. So the neuron size is about 700 micrometers. So the D2N can realize the tunable, the single passband or dual passband, the spectral filters, and the spatially controlled wavelength demultiplexing. And the right one is the D2N working under the visible wavelength. So in this case, the neuron was processed by the photolithography, each processed on a silica substrate. So the average size is around 4 micron. So each layer of the area is 4 millimeter by 4 millimeter, and the distance among the layers are 5 centimeters. So it used to recognize the handwriting digits from 0 to 9 at the visible wavelength around 632 nanometers. This is a 5-layer D2N, and the output plan was the intensity was detected by the CCD. So the obtained the simulated classification accuracy is around 91%, and the experimental accuracy is around 84%. So the neural size is a crucial parameter for the D2N. So especially when you aim to integrate it into the devices, so such as for example, the on-chip integration. So in this case, we must consider the size match issue between the D2N and other devices you want to integrate. So in the on-chip integration, usually the device is micro size or beyond the micro size. So in this case, there's no way to use D2N with centimeters by centimeters to realize such the integration. So the scale down the neuron size is quite important. So our group has presented such the AI photonic device with a single layer hologram neurons. So the polymer columns you can find was fabricated by the laser lithography. So the diameter of each column is around the 410 and 400 to 420 nanometers with different height levels. So the minimum difference among the levels is only the 10 nanometers. So by this kind of the super resolution fabrication, we can get a D2N for the data processing. It's trained to perform the optical inference tasks. So the one task is to recognize the correct key against the other random keys. So the keys belong to 3 different classes of the handwriting letters. So finally, we can find that the D2N can visibly communicate the acceptance or the rejection of the input key. Another task is a kind of the circle display showing the image of butterfly in the output plane only if the correct input key is given. So as we can see, in both of the 2 tasks, the experimental results can fit the theoretical expectation quite well. Okay, in 2009, we published, our group published a review paper in the light science and applications. So in this paper, we provide a detailed calculation regarding the relationship between the neuron size and the volume, the density of the neuron. So generally speaking, we can have a look at in this graph the light blue curve and the purple curve. So generally speaking, with the decrease of the neuron size, we can find the increase of the areal density or the volume density of the neurons. And it's an interesting phenomenon is that if the neuron size can decrease to 1 micron or even beyond the 1 micron, we can find such kind of increase in the density could be turned more rapidly. Yeah. So it means that so it's quite crucial to develop the nano lithography to fabricate the artificial neurons for the D2N. So actually, we did some work. We have some experiments in such an area. So because we always think that the development of the nano lithography technology actually is the basement technology for the fabrication of the AI photonic devices. So one is published in 2013. We use the two-beam laser lithography to get the water record resolution. So two-beam, one is to realize the photo induction, and another one is the donut-shaped beams to inhibit the photo induction. And finally, we can get the water record resolution of around 9 nanometers on the polymer. So this kind of technology can also realize 3D printing. We can find that there is some SEM images to show that the ability. And this year, we published the paper in Science Advances. It's about the laser lithography on the graphene oxide thin films. So we combine with the up conversion nanoparticles onto the surface of the graphene oxide thin films. And once the thin film can be irradiated by the light, so the electrons can generate through the up conversion nanoparticles and transfer to the surface of the graphene oxide and lead to the reduced reaction on the graphene oxide. In this case, we can get the resolution of the reduced graphene oxide is only around the 20 nanometers. So this is kind of technology we developed could be a basement, could be a base to further let us to develop the AI photonic devices. Also, previously we talked about the D2N, we can find that we decrease the neuron size. So previous the investigation, they can decrease the X direction and the Y direction into the macro size. But the Z direction, so means the height, also several tens or several hundred macrons. So actually, the aim is to decrease all of the 3 directions X, Y, Z to the macro size or beyond the macro size. So we have done some initial studies on the laser lithography of the graphene oxide thin films to realize the D2N neurons of the D2Ns. So we can find that we use the algorithm to design such the structures. The structure is on the GO, the graphene oxide thin film with the thickness around 1.6 microns. So you can find that we split it into the multiple pixels, and each pixel we can have the different heights. This kind of structure can be produced by the laser lithography. So we have do some simulation. We can find the accuracy under the exposure above the 10 times can reach above the 70%. So next, I would to talk about the D2N integration. So we also did some study in this area, published this year in the Light Science Applications. So we printed the D2N on the CMOS chips and compare with other technologies such as the CCD sensors, and the CMOS can show the faster and more energy efficient and cheaper, and already widely used in the modern consumer products. So if we have a look at the SDM and the AFI image, we can find that we print the D2N on the CMOS sensor, and the image grabbed by the CMOS can confirm the optical quality of the D2N and the ability to decrypt the K image with an accuracy around 100%. So actually it opened the door for the complete new generation of fast and power efficient D2N integration. So very recently we noticed such as the reconfigurable D2N work. So this is published in Nature Photonics. You can propose such as the reconfigurable diffractive processing unit, and the refractive actually achieved by the adjustment of the SLM, the special light modulator. The SLM is actually the refractive liquid crystal on the silicon. So each size is around 9.2 micrometers, and it can have 8-bit accuracy. So because we can adjust the phase on each pixel of the SLM, so we can realize the dynamic change, the dynamic and reconfigurable the D2N, and then they show you can find the picture, the figure. So they use here are the two videos, so each for one action. So this one is the jack, and another one is the walking. And jack and walking from different database, and each contain the multiple images. They input the image one by one and use the algorithm, and the DN can be optimized automatically. And finally, it can recognize both of these two actions. Finally, provide some outlook. So we talk about the broadband development of the D2N. It can expand the working wavelengths, especially if we can it can work under the visible range. Actually, it can be used to recognition the real picture, the picture in the real world. We also talk about the scale issues of the neural size. If we can decrease the neural size to macro size or even beyond macro size, you can realize the on-chip integration. And also another issue, the reconfigurable. If we can realize the reconfigurable, it means that we can get the time-dependent D2N. So current D2N, it can just recognize the figure we are inputting. It cannot recognize the figure we inputted several seconds ago or several minutes ago. So if we can realize this kind of actually this is a memory function. So it means that the D2N can be the in-memory computable sensing devices. So actually this kind of in-memory computable the sensing devices we can call the burn-like the chip integration, because you know the neurons in the human beings, brains actually each neuron can conduct the memory work, and both the memory work and the computing work. So it's why the human beings brain it can consume the much less energy than the computer. So it's why so finally we need to develop such the AI photonic devices. So this kind of burn-like the burn-like chip integration pathway for the green future for our society. Yeah, that's all my presentation. So thanks for listening, and thanks the conference organizer for the great work. Yeah, thanks.
Okay, thanks Professor Chen for this wonderful talk. And due to the time issue, I think we probably get one question for you. So regarding the graphene oxide material for the diffractive neural network, and in your results, you present one singular graphene oxide to illustrate the function. So how the Lie numbers influence the accuracy of the network?
Generally, if we increase the layer numbers, so the accuracy could increase. Yeah, definitely it's required. But actually, a practical issue because if we increase the layer number, so we need so it could be lead to another difficulty because we need to avoid the distort of each layer. We need to each pixel by pixel to fix the positions very carefully. Otherwise, it cannot realize such the AI recognition functions. So currently, we try to optimize the single layer, the D2N. Yeah.
Okay, thank you very much. And so we have to move to the next speaker, and let's thank Professor Chen again. So the next speaker is Professor Fan Zhang, and Professor Fan Zhang received his PhD degree in 2000. Professor Fan Zhang received his PhD degree in 2008 from Fudan University, followed by 2 years of postdoctoral in University of California at Santa Barbara. He became a full professor in Fudan University since 2013. Professor Zhang has authored a number of book chapters, patents, and research papers in international journals such as Nature Nanotechnology, Nature Communication, JACS, and other journals. And Professor Zhang submitted a recorded presentation, but he is connected online, and there will be the question and answer session at the end of this talk. So maybe the organizer can play the video.
Hello, good afternoon everyone, and today is my great pleasure to give this talk to introduce some of our most recent progress for the second near infrared window in vivo bioimaging. At first, I would like to introduce the background. Okay, for the pre-operation, the CT, MRI, and PET has been used in a lot of hospitals. However, it's CT and PET and the radiation is still a big problem. MRI and it's always take a long time to get the final signal. So the people are looking forward to using some new technology to realize the dynamic real-time the bioimaging. The fluorescence is a very important technology, and for this requirement, and fluorescence especially, and we use some near infrared fluorescence. We can get very deep tissue penetration, and we can realize some dynamic rapid imaging for some the blood vessel, and some as very fast signals. Another very useful application for the fluorescence and the bioimaging is the imaging guided surgery, as shown in this picture. And this is Da Vinci robot, and the surgery doctor, they can use this robot to operate some very delicate operation. And so here is the mechanism of this imaging guided surgery. Before this operation, and the surgery doctor, they can inject this and it's our chemical probes inside the human body. Always, sometimes we will inject it before the 1 week of the operation. So in 1 week, this probe and will provide with some protein and to deposit in some the disease site, and in the normal tissue it will exclude out. And with the time after 1 week and before during the operation, the surgery doctor, and they can observe some tumor and some disease sites with the luminescence here. So and it can realize very precise as a surgery operation. So up to now, and only one and FDA approved the probe. It's called ICG, and the indocyanine green is called ICG, and the excitation wavelength is 800 meters, and the emission wavelength is 810 nanometers, and it's in the near infrared window. However, and from this figure B, you can find that, and for the different tissue, the skin and some other tissue, muscle and the brain tissue, and you can find that with the extension of the wavelengths, the scattering the tissue scattering will be decreased a lot. So, and that means if we use the longer wavelength excitation, longer wavelength emission, we can realize the deeper tissue penetration. And from figure C, you can find that there's some absorption spectra here. And in the human body, the series absorption from the water, and the one peak is around 1,000 nanometer. The second peak is around 1,200 nanometer. The third peak is around 1,400 nanometer. So if you choose some emission or an excitation wavelengths beyond this, and 3 and the water absorption peak, and you can get the better penetration depth. So for the figure D, it's the autofluorescence. You can find that autofluorescence will decrease a lot when the excitation wavelength is beyond 1,000 nanometer. So so that's why that people want to use the longer wavelength to do some of the bioimaging. So from this figure, you can find that usually, and from the 700 to 900 nanometer, we call it the first near infrared window. From the 1000 to 1700, we call it second near infrared window. So in the second infrared window, so here we can find that the penetration depth and resolution will be increased a lot. And the limitation is the second infrared window development is the in-gas detector before, but now this kind of detector has been commercialized in lots of companies. So we can use this. It's very useful CCD detector to do this and the bioimaging work. So the near infrared 2 and the window, the pioneer work, and was first reported by the Hong Jie from Stanford University. They used the carbon nanotube to realize this work. And in the same issue, and Shu Mingyan write the views and news, and they raise this and the concept second window for in vivo bioimaging. However, actually, and before this work, and this work was published in 2009, and before this work, and in 2003, and M.G. Bamendi and the Franklin group, and they have published this work, but and they use this calculation, and they just anticipate, and they maybe as if we can get to the longer wavelength probe, and we can realize the deeper penetration imaging. But then they cannot synthesize this longer wavelength probe. It is just to do some of the calculation, and this is also a very important work. So in Hong Jie and manuscripts, it also cites this very important reference. Okay, so up to now, and there are 4 kinds of probe for the near infrared window. It's bioimaging. The first one is the single wall carbon nanotube. It's not multiple. The single wall must be single wall carbon nanotube. The second one is the cotton dots. The cotton dots and the M.G. Bamendi and from the MIT, and they dedicate a lot for this research area. Now they can synthesize lots of longer wavelength emission and cotton dots. They can also realize the multiplex detection with a different emission peak. For example, here they can observe some the brain tumor. The green one is a brain tumor. The red one is a normal blood vessel, so they can observe it and very clearly. The third one is organic dyes, and then the last one is rare earth-based nanoparticles. So in my group, and we focused on the rare earth and organic dyes and the research. So at first, I would like to introduce the lessenite near infrared 2 probes for bioimaging. So that's why we need lessenite for this research area. From this figure, you can find that. And when we dope the different lessenite elements and into the matrix, and we can realize the different emission. And for example, and here is a very useful one is the erbium. The erbium, and you can find here, and we can realize the 1,500 nanometer emission. Another very important one is ND. ND, we can realize the efficient emission around 1,060 or the 1,300 like that. Okay. Not only the emission, we can also tune the absorption wavelengths when we dope the different rare earth elements. And another important and advantage for the laser light probe is you can find that the emission peak is very narrow. And so this is narrower than the cotton dots, narrower than some organic dyes. So we can do some of the multiplex detection with this very sharp signal. So here we can find that, and we can use this rare earth nanoparticle, and we can tune the excitation and emission wavelengths. It's very easily. Okay, so another one is the small molecule near infrared window for the bioimaging. So this is the very new review article dedicated by my group, and we summarize the recently reported the near infrared 2, the small molecule probes, and you can find that, and the x-axis is the wavelength, the y-axis is brightness, and we are looking forward to get some probes and with longer wavelengths and there's bright emission efficiency. So, and up to now, and we have in my group we have got a lot the 5 series and small molecule probes. The first one is named with the Fudan University, the FD. This molecule is a very small molecule and is similar to the ICG, but we can realize the excitation emission beyond 1,000 nanometer. The second one is BTC, and the BTC is very stable structure, and we can use it to do some of the biosensing, that's pH sensing. And the 6 series is also it's a wavelength tunable series, and the probes. And LZ is a hydrophilic, and we can realize long-term and the blood and circulation. So it's also very useful probe. The last one is the D-body pi series. This one is the most stable one, and and after a long time, the laser excitation is no blinking, and so it's very stable as a probe. So the first one I would like to introduce the FD and the series probe, and the FDA, and in my group, and we developed this FDA and the 1008 and probe. And this probe, and you can find the incorporation to the FDA probe, ICG probe, and the structure is very similar, and the molecular weight is very similar. But our wavelength has been extended about 200 nanometers, and the excitation and emission are beyond 1,000 nanometers. So with this long wavelength excitation and emission, you can find that we can get better resolution, get a better tissue penetration in comparison to the shorter wavelength excitation. So, and we also find, and when we put this small molecule into the micelle and assembly Easterm, and we can realize the J aggregates. And the J aggregates and can be formed by the aggregates of this small molecule, just like this structure. And after they form the J aggregate, you can find that we can get the excitation emission wavelength is beyond 1,300 nanometer. With this very long wavelength excitation and emission, and we can get better resolution and better penetration. Okay, so, and in my group, and we also developed some small molecule probes for the near to the biosensing. So this research area is also very important for our the analytical chemistry. And the first example is that we can use our probe to detect ROS and RNS sensing, and we can use some the drug-induced injury model as a small animal model, and we can detect the ROS in real time. And another example is the pH sensing, and we can detect the different the pH values in the small animal, the body, and with different model. However, this biosensing work is very complicated because, and we summarize as shown in this slide, we summarize some of the parameter you can find here in the human body, and the pH value, the RS and the RNS, and in different tissue and in different the organ and in different disease, they are totally different. So it's a very complicated detection process. So for the probe design, and it should be very careful. So if you focus on some organ or some disease, and you must and follow there and the target. So the biosensing work is very complicated work. And another example is how to realize near-2 imaging and without radiation, and we can realize signal to noise ratio. Okay, so we can, and the most important one and is the bioluminescence. And previously, and the people try to find some protein from the nature, for example, from jellyfish or from some firefly. They can find the lucifers, and they can realize this reaction to realize some the excitation free and the emission is the bioluminescence. But how to realize the near-2 bioluminescence is very challenging, and we try to synthesize some small molecules to interact with the protein, but it's very difficult because if the molecule size is too large, it's difficult to interact with some luciferase protein. So, and we try to use this method, and we put the different organic dye, CY5, CY7, and we also synthesize this FD and 1029, and we put this organic dye and together, and we loaded it into the Easterm and with the luciferase modified on the surface. So we can realize that the BRET and FRET, successive FRET, so we can realize near-2 the emission, but it's still nanoparticle. We cannot translate it into some the leaf cell. So it's still a lot of things to do. But with this probe, you can find that because we don't have to use the excitation laser, and it's excitation free, and so you can find that the signal to noise ratio has been increased a lot for the tumor imaging, and for some other the ATP mediated material space tracing is very useful. Another example is the persistent luminescence. Persistent luminescence has been used a lot, and usually in the visible and the region. And for example, the mechanism is just very excited with these materials with some UV or with some X-ray, and they can deposit some energy into some defect. And after you remove the excitation and some the electronics, and they can release out from these traps. So you can realize the long-term and persistent luminescence. So purposely, as people try to use the near-infrared persistent luminescence to do some bioimaging. For example, this work and from the Sherman group, and they synthesize this. It's a very large size and materials. And after they use the mechanical finding and process, they can get this as small size particles, but aggregation is still very serious problem. And they inject these materials and into the small animal, they can realize the in vivo bioimaging. The emission wavelength is 690 like that. So so we try to synthesize some of the nano-sized, the very dispersible nanoparticles, and so we found that, and if we use this fluoride and various nanoparticles, if we use the X-ray activated, and we can realize some X-ray activated persistent luminescence. And when you remove the X-ray, and we can realize very long-term persistent luminescence, and can last about 72 hours and for this. And if we dope the different elements, we can realize the difference near 2 emission from 1500 to 1060. So, and there's some the synthesis is optimization because of limitation of time. I don't have talk it here. So, and with this kind of materials, most important, we can synthesize this single nanoparticle multi-layer and persistent luminescence. We can do some barcoding, and we can also inject these materials into the small animal, and we can observe the blood vessel. We can observe some other disease. So it's very, very important and materials. Okay, so and because of the limitation of time, and I have to stop here. And thank you for your attention. Thank you.
Okay, let's thank Professor Zhang for this recorded video. And since Professor Zhang is not connected online, and if you have any questions, you can contact him directly via email after the end of this session. So now we move to our plenary talk by Professor Isabel Stout. So Professor Stout is currently the head of the Amy Noether Research Group at the Institute of Applied Physics, University of Jena, Germany. She is an elected member of the Faculty Council of the Faculty of Physics and Astronomy at the University of Jena, a member of the German Young Academy, and a member of the management board of the Collaborative Research Center, the Linear Optics Down to Atomic Scales. Dr. Stout's research focuses on the use of designed photonic nanostructures, which are to control the emission, absorption, and the propagation of light at the nanoscale level. So now I will give the floor to Professor Stout. Professor Stout, so can you start if you're ready?
Yes, thank you very much. I will share my screen. Oh, all right.
Okay.
And can you see my slides well?
Yes, we can see.
Okay, perfect. Then I would start now. Yeah, so thanks a lot for the kind introduction, and also, yeah, thank you to the organizers, in particular to Professor Minggu for inviting me. It's a great honor and pleasure to talk at this symposium today. Yeah, and yeah, as you heard, my name is Isabel Staude, and my topic today is resonant metasurfaces empowered by two-dimensional materials. Yeah, so all the work that I'm going to show is, of course, a team effort. And here I just want to highlight my key collaborators. I'm collaborating both locally with the groups of Professor Andrei Tuchanin, who is growing all the two-dimensional materials, or most of them that we're using in our work, and also the groups of Falk Eilenberger, Frank Setzmann, and Thomas Perch here at Friedrich Schiller University of Jena. And we also intensely collaborate with Australian National University here, in particular with the groups of Dragomir Neshev, who has also given a talk in this symposium already, like earlier in this session, and also with Yuri Kivsha's group. All right, so this is the outline of my talk. There will be a motivation introduction where I will basically introduce the two components that we are to combine, namely the metasurfaces and the two-dimensional materials. Yeah, and then I will talk about several research topics or several projects that we did in the recent past or that are ongoing on light-emitting metasurfaces and nonlinear metasurfaces utilizing these two-dimensional materials. And if there is time remaining, I also have another topic on ultra-thin metasurfaces in the end. Yeah, there will be very short outlook. Yeah, so let's dive directly into the topic. So. And allow me to give you a short idea of what an optical metasurface is. There was already a talk by Dragomir earlier in the session, so I guess you are already well prepared, but it will be quite short. So a metasurface is basically a sheet of nanoscale thickness, which is here oriented out of the plane of your screen. And now we come in with a known input light field, and the metasurface transforms that into an output light field with desired properties such as spectrum polarization and wavefront. So how does the metasurface do this? So it's basically a two-dimensional sub-wavelength arrangement of designed nanoscale building blocks. And we can approach this concept of the meta surface from two sides. Like many of you are probably familiar with the concept of optical metamaterials, where designed building blocks are arranged in a three-dimensional fashion, giving materials with effective optical properties, and the light waves can average over these over the scattering response of all these different building blocks and produce some effective optical properties, including those that are not found in natural materials. So the metasurface would be basically the 2D material counterpart of a metamaterial, so just a single layer. And the other side we can approach these metasurfaces from are optical nano antennas. So nano antennas are basically efficient links between localized near fields, optical near fields, and propagating light waves. And if we arrange many of these nano antennas in a two-dimensional array, then we can also end up with a metasurface. So metasurfaces have been really in the limelight of nanophotonics research in the last decade or so, because they mainly because of their capability to allow for wavefront control by imposing a position-dependent phase shift onto an incident light field. So here I just depict a very simple example. Again, there's the metasurface here out of the projector plane. Then we come in with some plane wave, for instance, and now in this case is the example that these building blocks, or meta-atoms we sometimes call them, impose a linear phase gradient just by their design, the design of their scattering response. And in the case that this is a linear phase gradient, this would just lead to a deflection of the incident light wave. And along the same lines, of course, much more complex functionalities, wavefront shaping functionalities can be implemented, including such holographic imaging, like here, this is from the group of Andre Faraon, or also from Federico Scarpasso's work, who showed, for instance, such a achromatic meta lens. So there are several ways how or what these meta atoms can actually be. There are different mechanisms to locally impose this phase onto the incident light wave. Here I'm showing two examples from the literature, like these are like basically upright standing little waveguides, and here a geometric phase is employed. One consensus in the literature is basically that for high efficiency devices, one should use dielectric materials in order to not absorb too much light. But there are also, for instance, plasmonic metasurface, and the field was actually started for them, and sometimes they are still very useful. So in our case, in most works that I'm going to show you, our metasurface consists of high index dielectric nanoparticles, which support localized Mie resonances. So they really exhibit a series of electric and magnetic multipolar modes that are supported by these little building blocks. And if they are spherically shaped, then these modes can be described by Mie theory, which is already more than 100 years old. Typically in our experiments, they are not spheres, but have different shapes, but still they exhibit very similar resonances that can also be developed into the Mie scattering contributions. So this is very useful because we have both electric and magnetic modes, so we can also interact both with the electric and the magnetic component of a light wave, which gives us exquisite control over light waves. And also because, again, these building blocks are dielectric, we have very low losses. And now by tailoring size, shape, and material composition, we can really tailor very carefully the response of the building blocks and the metasurfaces. So using such high index dielectric nanoparticles as building blocks, in the past we showed a few functional passive meta devices, like we started with such a Gaussian to Vortex beam shaper that basically produces a vortex beam from a Gaussian beam. Then we a bit more later we made a holographic metasurface, which basically produces an image of these letters H nu behind the metasurface. And a bit more recently, we also showed a metasurface that create such a helical point spread function, and by imaging through such a phase mask, one can derive with suitable image processing algorithms and 3D information of a scene. So this was together with Frank Setzman's group. So this works all quite well, and of course one can have other examples like lenses, other holograms, beam deflectors, and so on. However, So the efficiency are also quite high, like experimentally we reach over 80% transmission efficiency. However, yeah, you can now still ask me or challenge me and say, like, why should we care about these? I mean, you showed us also other approaches. What is special about your approach? And so what we are I want to make a little detour here and just tell you of some experience that I had when attending an industry meeting. So basically, I was giving my talk on metasurfaces, and then afterwards a lady from industry asked me, okay, Dr. Staude, but now which surfaces of a smartphone would you want to replace by your metasurfaces? And for me, this was a very, like being a more fundamental scientist, this was a very applied question, yeah. And the first thing I had to think of was, oh, well, we can do very nice photonic color with them, but well, I don't think this is what the funding agencies will pay us for. So what I really think is that by pushing metasurfaces towards being tunable, also light emitting and showing nonlinear properties, we will be able to access much more application potential. For instance, one could have adaptable lenses, one could have smart displays, one could have projectors, or even maybe devices in direction of 3D imaging, quantum communication, and so on. So I think this is really one direction which is very important in metasurface research. And if we think now about these tunable or active metasurfaces in general, like tunable, light emitting, and nonlinear is what I mean by active, then these resonant metasurfaces composed of mirror resonances have really a high potential. So because of their resonant optical response, they show inherently show a strong spatial and spectral dispersion. This gives us not only the opportunity to tailor frequency and angular sensitive optical responses, but also to facilitate tuning and switching in these structures, as it's much easier to tune something with a strong spectral dispersion. Yeah, but also because of the local resonances in these building blocks, they also resonantly enhance the electromagnetic near fields. Basically, each meta atom acts like a little nano antenna and can enhance the electromagnetic near field, and thereby any kind of light matter interactions, which can be nonlinear optical effects, spontaneous emission, but also your favorite light matter interaction effect you're thinking about. So in this talk, I will mainly concentrate on nonlinear optical effects and spontaneous emission. And but generally we'll discuss now active metasurfaces that are tunable, light emitting, or nonlinear. And so now the challenge will be to integrate. So most metasurfaces are made from like high index dielectrics, like often silicon, titanium dioxide, like usually semiconductor materials with a high refractive index but low losses. And not always these materials, or in rare cases, actually, these materials give us the functionalities that we need for these active metasurfaces. So one attractive way to add active components is to combine metasurfaces with two-dimensional materials, in particular two-dimensional semiconductors. So in general, 2D materials are materials that consist of just a single layer of atoms or molecules, and there are hundreds of different species. Like the most well-known is graphene, which also produced the 2010 Nobel Prize from Novoselov and Geim. However, despite its huge success, graphene is a semi-metal, and this really limits its applications in electronics, and in particular also optoelectronics. And so two-dimensional semiconductors, ideally direct bandgap semiconductors, are needed. And here the promising class are two-dimensional transition metal dichircogenide, or TMDs in short. And here I just show the general structure of them. So they have the sandwich structure with the chalcogen in the middle, with the transition metal in the middle layer and the chalcogens at the outer layers. They have an asymmetry break in their structure. So but as an important feature, if you thin them down to the monolayer phase, they feature direct electronic band gaps. And the nice thing now of 2D materials in conjunction with metasurfaces is that the two are ideal for integration because they both have this two-dimensional nature. So putting a 2D material on top of a metasurface is basically like putting a slice of cheese on a bread, if you allow me this this picture. All right, so just a few more interesting facts about these 2D semiconductors. So in the 2D TMDs, conduction and valence band edges are located at not at the center of the brilliant zones, but at the corners, namely at the K and K prime points of the 2D hexagonal brilliant zone. So it looks a bit like this, yeah, taken from this reference given below. And yeah, these two valleys at K and K prime, they are inequivalent due to the inversion symmetry break in the crystal structure of the material. And this leads to valley-dependent optical selection rules. So basically the interband transitions become spin-dependent. And yeah, this we can see then, or the observation that we immediately have is that the helicity of the photoluminescence from these materials follows that of the excitation light. So if I pump it with left-handed circular polarized light, it will, under the right conditions that preserves this valley polarization, also emit left-handed circularly polarized light. So these 2D materials also offer strong second-order nonlinear response, about an order of magnitude more than what you would get if you thin down a typical nonlinear material down to the monolayer phase. And also both the photoluminescence and the second harmonic can be tuned by electrical gating. So altogether, in my view, it's very attractive to combine these two systems. Like on the one hand, the metasurfaces can enhance the interaction with the ultra-thin material by subwavelength light concentration and thereby help to exploit their properties. And on the other hand, the 2D TMDs act as light-emitting nonlinear and tunable components, which can make metasurfaces active in different ways and thereby also broadly enhance their scope. Yeah, with this, I come to the first results part, if you want, of my talk, so which is on light-emitting metasurfaces. I show you again this cartoon, and now for light-emitting metasurfaces, what we want is we basically want to get rid of this known input light field and have the metasurface by itself emit a desired light field. And basically we consider for this the metasurface as an array of resonant dielectric nanoantennas which are driven by localized sources. And one of the challenges, of course, the integration now of the light source in the metasurface architecture. And here we want to do this by combining them or by hybridizing them with 2D materials. So what can the metasurface do or help? So on the one hand, it can lead to a brightness enhancement of the emission. I will not go into all the details of this formula here, but basically the fluorescence count rate from a 2D material which is sitting on top of the metasurface can be enhanced by excitation enhancement, quantum yield enhancement. Also the extraction efficiency can be enhanced by the metasurface, and the collection efficiency, basically directing the light more efficiently towards the detector. And also the metasurface is very good at directional shaping. So the nice thing is that here we have both the effect of the array or arrangement in the metasurface. So this was already explored quite a while back in plasmonic arrays of such plasmonic dot particles. And I will show a few of such images. So this is not our work, this is just a reference, but these type of images here are back focal plane images. So we're basically imaging the back focal plane of the collection objective. And each point in here corresponds then to a direction of emission. Yeah, so the center is normally out of the substrate plane, and all other directions are then so the outer ring is basically the angle corresponding to the numerical aperture of the objective. I just explained this because we will see a few of these images. But we will also have the antenna effect from the individual meta-atoms, and even a single meta-atom, if designed appropriately, can already have pronounced directional shaping effects. So together, it's a bit like scattering in solids. We can consider a form factor and a structure or array factor. And together, we have many degrees of freedom to tailor directional properties. So the first work that I want to show you is a silicon metasurface exhibiting me-type resonances, which was hybridized with two-dimensional MOS2. And these flakes that we're putting on top, they are CVD-grown monolayers, which are transferred then by a wet transfer process on top of the metasurface. So this is how the structure looked like. So the metasurface is this darker field, and now the monolayers are these greenish areas. They often have this triangular shape. This was quite an early work. It's a while back that we did this. By now these flakes have become larger, and the transfer a bit like the intact areas have also become larger. Yeah. So what we did here was we fabricated a series of metasurfaces with a variation of the nanocylinder diameter d, thereby sweeping the Mie resonances over the emission bandwidth of the MOS2. And then here in the first experiment, we looked at the spatially resolved photoluminescence from these structures, and we could immediately see a significant enhancement of the emission of the MOS2 whenever it was on top of the metasurfaces. So the metasurfaces are always here within these dashed areas, and I mean the monolayer flakes I think you can see quite well, and you see they are much brighter on top of the metasurfaces than next to them. We also looked then in the back focal plane, and we could find very good reshaping also of the emission from this light. So basically the metasurfaces have different diameters and they get more resonant or shifting, the resonance is shifting more towards the maximum of the emission as we enhance the diameter here. And you see as this happens, the light is basically changing from being directed sideways towards being directed out of the metasurface plane, normally out of the plane. So what I should say here is that this enhancement effect here is absolutely not dominated by a photonic enhancement effect. So one has to be very careful with these two-dimensional materials. Is there a question or? Okay. Because the emission properties depend also very sensitively on the environment. And here we could also show that this is mainly due to basically reduced quenching by the substrate. So the substrate basically dopes the 2D material and also induces some microscopic strain, which is why now the emission is brighter when the 2D flake is sitting like freely suspended on top of the metasurface. So one has to be really careful when interpreting such enhancement effects, and that's also what we learned from this study. So now I want to talk a bit about utilizing this valley degree of freedom in the 2D materials, because I think it's a very interesting question now, like how these chiral local emitters can now couple to engineered nanostructures. Of course, we're not the first ones looking at this interesting problem, so I show you a few works from literature showing, for instance, separation of valley excitons, valley selective optical control by nanostructures, and also spin selective excitation of directional flows of polaritons. And I'm also aware that there is a big research effort in Beijing on these kind of systems in individual nano antennas assembled by AFM, for instance. And so what we wanted to do here is, so in our experiments, we wanted to pay particular attention to analyzing the influence of the handedness of both the excitation light and the detected light on the properties. So in contrast, in the literature and all the works I show here, it's sometimes assumed that by characterizing the chiral properties of the emitted light only, one can effectively separate the light emitted by excitons located in the K and K prime valley. However, even for non-chiral emitters, chiral light emission of opposite handedness can be directed into opposite directions by suitably designed nano antennas. So for a mere change of detection polarization, the effect of valley routing is basically indistinguishable from just simple spin momentum locking emission phenomena in such systems. So in order to disentangle now these influences of like handedness of excitation and detection light, we were looking at a system inspired by this work from Dragomir's group. Hai Tao here designed such a nano antenna, which basically has a quadrupolar mode in this longer bar and a dipolar mode in this shorter bar, and together they can interfere to direct light from a spinning dipole. So this is a numerical work. So from a spinning electric dipole into different directions in space. So we collaborated again here with Dragomir's group, and they basically, we were looking then at such systems. So you see here the metasurface composed of such gold nano antennas in this case. So this is now plasmonic implementation here, and here you see the cathodoluminescence imaging clearly showing the dipole and the quadrupole excitation in these structures. They were designed then to overlap with the excitonic emission from a WSE2 layer sitting on top of this metasurface at cryogenic temperatures. So, but here as a pre-characterization, we are first looking at their properties at room temperature. So basically, the nano antennas are not designed for room temperature emission. So, so this is just a pre-characterization, but we already see that the two systems are interacting. Basically, at these, if we cool down the system later on, the emission peak will shift towards the antenna resonances. Here it's off resonance, and the nano antennas basically lead to a quenching effect. So you see each nano antenna as a little dark spot at this emission mapping here. And here's also the spectroscopy. So we see there's no big influence of the nano antenna on this emission now. But if we look in the emission lifetime measurement, we can see that the nano antenna actually already couples quite strongly to the 2D material, and the lifetime is significantly reduced. So now we go to the measurements at 4 Kelvin, where the nano antennas are designed for, and we can compare here. So this is just the spectroscopy of the emission. With the nano antenna, we have slight enhancement compared to the monolayer on the bare substrate, and we checked also that the valley degree of freedom, which is defined here, so this is preserved on top of the nano antenna. So it's quite high in general. About 65% for the bare monolayer, and about 45% is still there for measurements taken on the nano antennas. So this is a prerequisite for our study, that we have this valley degree of freedom and can selectively couple now these chiral emissions to the nano antenna modes. So finally, here I show the backfocal plane images for different excitation and detection helicities. So it's like a little table. We have the excitation helicities here and the polarization helicities here. So on the left side is unpolarized, and we have sigma plus, sigma minus, and you see already like both excitation changing and also polarization changes, and also detection polarization changes lead to changes in this emission pattern. To make it a bit more clear, we look at the relative difference images now upon excitation helicity switching here, and we see that so what many other works already showed was to change the detection polarization and see changes. But now, even if we detect unpolarized, we still get a significant contrast in the emission. So this difference image tells you basically that if I switch the excitation helicity, the directional properties of emission will change of the system. Yeah, so, and this is important because it basically shows now that we can selectively excite an exciton population either at the K or K prime valley, and this then couples to the nano antenna in a selective way, giving a particular emission pattern. So we believe that this is really important when thinking about valleytronic applications, where this valley degree of freedom is used as a degree of freedom to encode information. So with this work we contribute to showing that nano antennas can or also meta surface can locally address, read out, and manipulate this valley degree of freedom. And of course we want to keep working on this and improve this further. So, one thing to improve actually would be to have the 2D material only in the desired region where we, for instance, have the hotspot of our nano antennas. And one thing we did here is to look at nanostructuring of the 2D materials using focused ion beam milling. So I'm giving here a few technical details, which I don't want to discuss in detail now. But and also here you see, so the process is quite sensitive on the exact parameters that you use for the focused ion beam milling. And then we can basically, here's an AFM scan of such a pattern region where we just milled such a grating of a period of 100 nanometer into this film. Then also looked at the photoluminescence from these images. We could see, of course, in the pattern region, the emission was reduced, but still there. Of course, we also reduced the amount of material, so this is quite expected. We could see also a blue shift of the emission maximum with the ion dose. So the thing we were most interested in is if the valley polarization will still be preserved if you use this method to mill or to locally remove this material. And this slide here shows that this is the case. So the PL intensity is shown here for sigma plus and sigma minus emission for the unpatterned material, and then also for the material patterned with two different ion doses. And the valley polarization effect shows here in this region where these where we have a difference between the two curves for the two helicities. And here's also the degree of valley polarization as a function of the ion fluence. So we see it is reduced a bit, but if you look at the absolute numbers, there's still significant valley polarization. So it's only slightly affected by the nanopatterning. So we can still have, so we can basically get nanoscale chiral sources by this kind of method. And the vision here would be to make hybrid structures where the material is only in the desired regions, so that we can basically enhance the overall interaction of our nanostructures with the 2D material. Yeah, so now I come to the point of the nonlinear metasurfaces. And so nonlinear metasurfaces are, or mirror-resonant metasurfaces are actually quite ideal for looking at nonlinear optical effects, as Dragomir probably already explained very well in his first talk. So they provide a resonant near field enhancement and also high damage threshold. Whereas when we combine now with the 2D TMDs, they would provide the strong Chi2, so the strong second order nonlinearity. So here's again such a simple sketch, the kind of experiment that we want to do. Basically, we want to shoot now a beam at frequency omega at the hybrid metasurface, and then part of this will be converted into light at frequency 2 omega for the process of second harmonic generation, which is a basic process and also would be then similar to looking also at some frequency generation and other nonlinear processes. The real beauty of using metasurfaces for this is that no phase matching is necessary because they have a sub-wavelength thickness. And this sounds now easy, but if you ever did nonlinear optics experiment, you know that phase matching can be very difficult, and complicated. And basically if people, and to an extent that people would be quite happy to sacrifice also some efficiency in order to have this much more simple structures which give you a nonlinear signal immediately without complicated phase matching measures. So here I show first project which was done with together with Thomas Perch and Yuri Kivch's group. So here's the metasurface looks like this. So it's a silicon metasurface, and it's designed to operate with MOS2 monolayers, and it has such an interesting structure which gives us high quality factor modes. So here I show the linear spectra experiment and simulation, and we see for each polarization X and Y, we basically find one high Q mode. The Q factors are about 250 for this resonance and about 100 for this resonance. We can also look at the intensity of the parallel field components in the plane where the 2D material will be sitting in numerics. And what we can find here is that we have a strong enhancement of these field components, which will be in the relevant plane, which are also the relevant field components for second harmonic generation in these 2D materials. So now we looked at the second harmonic, and we saw that both resonances give us an enhancement, as you see here. There's also the simulation for comparison again. And but we see also like this higher wavelength resonance in Y polarization gives us a stronger enhancement in the second harmonic. The bottom images just show that the polarization properties are not significantly affected by the metasurface. So we compared also a bit more carefully different regions of the sample. So what we have here is basically regions with unstructured silicon, the resonant metasurfaces. There is glass in between, and also silicon metasurfaces, but which don't have any resonances in this range of interest. But the material would still be like freestanding on top of the resonators. There's one exemplary image how such a second harmonic scan looks like. So for instance, in this case, this was for X polarization, so for the shorter wavelength resonance. But here we see already that the emission here is enhanced in this region of the metasurface. And here's a bit more systematic. Note that this is a logarithmic scale where we compare now the normalized second harmonic intensity for these different regions and the different resonances and polarizations. And we find that the highest enhancement is really for Y polarization and the higher wavelength resonance. And also, just to give some numbers, the second harmonic intensity is enhanced by about 1,500 compared to unstructured silicon. But this may be not a fair comparison because silicon will absorb the second harmonic. So, but we still have an enhancement of about 35 compared to a non-resonant wavelength. So this would be the real pure photonic effect here. So what we wanted to understand, and maybe allow me to go back briefly, is we find the higher enhancement for the lower quality factor resonance for this higher wavelengths one here. Why is that? And this is something I want to discuss on this slide. So we basically looked now at the field distributions at the second harmonic wavelengths, which are shown here for X and Y polarization. And we see that because the silicon blocks absorb the light, the second harmonic is really located in the areas between, or enhanced most between these building blocks of the metasurface. And we compare again, you saw these images already. So this is again at the short wavelengths and the long wavelengths resonance, where we had enhancement in both cases, but we see that for the short wavelengths resonance, this enhancement is mainly on top of the silicon bars, whereas a large fraction of it is also between the silicon bars, like up to 50% of the total in-plane pump field is between the bars at this higher wavelength resonance. So this shows now the important role of silicon absorption and also of this spatial field profiles, and that they should be matched. Yeah, so you see that this field profile and this one are well matched. They both have high concentration of the field in between these silicon bars, and thereby we have a good mode overlap and yeah, the higher second harmonic intensity in the end. So yeah, this shows the importance of yeah, what we call mode matching, yeah, which basically replaces phase matching for such metasurface or yeah, such architectures. However, the good thing is that this mode matching can be done at the design stage, basically by the photonic designer, whereas the phase matching usually has to be done by the person in the lab each time they want to use the second harmonic. So this can be a real advantage. I see I don't have much time left, so I will just very briefly show this last project where we used our developed focus ion beam milling structuring method also to make ultra thin metasurfaces. So this time we were basically milling such grading structures into them and checked the second harmonic. So there's reduced second harmonic in this area again because we removed material, and actually it's a bit more reduced, but it's still significant. And so now we looked at the yeah, emission properties, like the emission pattern of the second harmonic from these kind of structures. So basically it was a grating period of 675 nanometer, whereas the excitation pulses were at 840. So at the excitation wavelength, this is a sub-wavelength grating, but for the second harmonic, it will be a diffraction grating. So here's also a zoom in, and if we look in the back focal plane at the emitted second harmonic, we can see this diffracted, like diffracted second harmonic in these structures. And to make something a bit more complex, we also made such a fork grating. You see in the inset here that yeah, there is like this bar is interrupted and the other ones are folding around it. And if we look then, this is creating vortex beams in the first diffraction orders of this structure. So you can see this as a very thin, yeah, just a one molecular layer thin metasurface structure, nonlinear metasurface structure. And I'm also citing this work, which was by another group doing something very similar. All right, I will skip this last topic in the interest of time. If you're interested in ultra-thin metasurface, write me an email. I will tell you and come to a very short outlook. So what we want to do is in the future to enhance complexity of spatial emission patterns, also use the dynamic control that the 2D materials offer to control the emission properties of the hybrid systems. We will look at electrical driving schemes, continue our fundamental studies for valleytronics, and also look at the integration now of nanostructured TMDs with resonant metasurfaces. And yeah, there was also like in 2020, we also published a review on combining near-resonant structures with two-dimensional TMDs in case you're interested. And yeah, with this, I come to an end. I want to thank my current team and funding and collaborators, and most importantly, you for your attention. And thanks again also to the organizers. And I would be happy about any questions that you have. Thank you.
Okay, let's thank Professor Start for your wonderful talk. on the matter surface integrated with the 2D materials. And now we can open the question and answer session. So the first question is regarding your nonlinear matter surface. So you present the structure silicon integrated with the MOS2 to enhance the second harmonic generation of MOS2. So how large is the field enhancement by the silicon matter surface? And if you compare it with the metal case, the plasmonic matter surface, what is the advantage of silicon matter surface?
Yeah, it's a very good question. Maybe I go back to the particular work. Here we have here we see the enhancement that we get in these structures. So on the right hand side, this is the enhancement at the pump wavelength. Yeah, so at the fundamental harmonic, and you see this is normalized intensity, and we get up to 130, 140 enhancement. The advantage would be that we can get high quality factor modes in these structures, like if I go back a bit more, there were also the quality factors of these structures are about 250 or 100. So you can even improve this more. It can be on the order of several hundreds experimentally, typically. And for plasmonic matter surfaces, I mean, I'm not saying they are worse, but the problem is the inherent losses. And they will always limit your Q factor. So with the plasmonic structure, it will be much harder to get high Q factors as they are absorbing, and thereby limiting the Q factors. What could be interesting for plasmonic structures is that they can also localize the fields very strongly. So But then if you think again about nonlinear experiments, due to their losses, typically they also have lower damage thresholds. So the dielectric structures, you can pump harder before they degrade. Yeah. So I mean, it depends a bit on what you want to do, what your application is, but I would say the advantages are the higher Q factors that you can get, and also the higher damage thresholds.
Yeah, thank you. So when you design the matter surface for enhancing the nonlinear effect, do you consider the multiple wavelengths, like the pumping wavelengths and the emission wavelengths, multiple resonance effect?
I think I didn't get the question.
So the question is, when you design the silicon matter surface for enhancing the nonlinear effect of the 2D material, do you consider the resonance behavior at the fundamental wavelengths and the emission wavelengths, both wavelengths?
Okay. So there's actually the resonances are only designed for the fundamental harmonic. For the second harmonic, this is more like, maybe I show these fields again. So there's no strong resonant response in this region of the second harmonic. We can still calculate the fields, but they also don't change very much with wavelengths in this range, which is also why we only show it at one wavelength. It's basically the same for the second harmonic of the two other resonances. It doesn't change strongly. So this is not a resonant behavior. This is just how the structure behaves here, but without a pronounced resonance. So with the resonance analysis, we concentrated really on the fundamental harmonic here.
Yes, thank you. So I think the last question from the audience is a general question. So where do you think the matter surface field is going?
Oh yeah, this is very open, and I think it's going in many directions. Yeah, so this is really hard to answer. Yeah, so what we see is, maybe this I can say, we get a lot of interest now also from industry. We were already approached by a whole by many companies that are active in Germany and in the area of optics, semiconductors, and so on. And they all have their own visions what they want to use it for. Yeah. And plus, I think also, I think like some examples, be careful what I say now, but are tunable devices. This is of high interest, tunable optical devices, also light sources and displays. So I think these are the things where we will see applications in the not too far future. At least the companies are now actually actively working with us and other groups, as I know, on developing things. But of course, being a fundamental scientist, there's also a lot of new research efforts that we can do. And I think especially when you think about metasurface combining with 2D materials, I think there are still many open questions how this coupling works and how this can be used in the context of valley polarization, for instance. But yeah, so this is really a hard question because there are still so many directions, research directions, and also application directions that this is not an easy answer. Yeah. So.
All right. So thanks, Professor Start, for answering the questions, and thanks for your wonderful talk. And this was the last talk of this session, and due to time issue, we have to close this session. So I'd like to thank once again all the speakers of the session and everyone who joined. And now we will have a break, and we'll be back at 12:15 with the sessions.
Okay, hello everyone. Thank you for joining our session, Advanced Imaging session. My name is Yang Yundou Wang. I'm currently a postdoc in IPC. It's my great honor and pleasure to be the host of this exciting session. The session will cover the cutting-edge technologies, topics in computational imaging, super-resolution microscopy, and integrated optics, which will be presented by outstanding speakers. Before we get started, I'd like to draw a few remarks about the session. It will include a 45 minutes plenary talk and 4 invited talks with 20 minutes each. I'd like to encourage you to ask questions at the end of each presentation. Okay, let's dive in. Okay, I will give a brief introduction of your research topics. As an interdisciplinary PI, his goal is to promote the development of knowledge in biophotonics, integrated optoelectronics, nanotechnology, statistics, and neuroscience. Today, he will present his latest research on deep compressed imaging. Let's welcome Professor Yang. The stage is yours.
Thank you very much. Also, thank you for the invitation. Thank you for Professor Gu. So you can hear me well, right? And see the slides well?
Yes, yes.
Yes? Okay, great. Thank you. So I will get started. So, so today my presentation title is the deep compressed imaging while optimized pattern scanning. So before I go into the detail of that, let's have a quick review of the landscape of different imaging modality. So basically, I will show 3 different imaging modalities. So the first one is the wide field illumination is the most popular one. Just like our eye or the camera, it's like a wide field illumination. So the advantage of this approach is a single shot. And of course, it's very fast typically, but it could be expensive in the non-visible wavelength range, for example, or in some scenario, this may not work nicely in case of tissue scattering or if you have a flock, right? So just like Professor Situ introduced just now. And then the other approach, it is full scanning. So instead of a wide field single shot imaging, in these setups, we will have point-by-point scanning of the object. So as a result, these different pixels, they are acquired sequentially. So the advantage of this approach is that potentially it could be a very low cost. We only need a single scanner and a single detector in this case. And then it's also compatible with laser scanning system for microscopy. But however, since it requires point-by-point scanning, it's not too efficient compared to the single shot, right? So finally, there's another approach, which is compressive sensing based imaging. So I think this has been introduced by Professor Situ already. So I will just go quicker. So basically, you have the object, and then we project different pattern onto this object. And then for each pattern, we will summarize all the intensity into a single detector. And then we go through different patterns. And then finally, we get many different single pixel measurement. And then we can do some reconstruction to recover the original object. So using the compressed sensing algorithm, this approach can be highly efficient. So meaning that we can do a substantial downsample while we can still recover a good image. But on the other hand, this approach is well for using the conventional compressed sensing or single pixel camera approach is relatively slow due to the low switching speed between different patterns. So typically, we will use DMD to do this switching, but this is unfortunately relatively slow. So our motivation is that can we have something that can be high efficient, like compressed sensing single pixel camera, and meanwhile we can do it faster. So we don't need the DMD. Can we go a little bit faster compared to the DMD? So here we want to combine the two different approach or the modality that I introduced in slide number 2. So we can still use the concept of compressed imaging because it's highly efficient. It has a fewer measurements. On the other hand, we also want to take advantage of the fast scanning approach in the point-by-point scanning. So we want to combine the advantage of both, and then to create something called a pattern scanning imaging modality. So in this scenario, we will scan a single grayscale pattern across the entire object, and then we can acquire the image pattern by pattern or block by block using a single pixel detector, and then we can do reconstruction. So in this case, let's say that if the image is like 100 by 100 pixel, if each block is 10 by 10, for example, then we would just need to acquire 10 by 10 measurement in total. So that in this case, the imaging speed can be substantially faster. And also because we are doing scanning, the overall speed can be fast. So here on the right-hand side, it shows more details. So basically, we only need a very small number of measurements to acquire the entire object. So it's relatively fast. So also, using this imaging modality, and we develop auto encoder reconstruction algorithms that we can jointly optimize this scanning pattern as well as the reconstruction algorithms, so that you can have high resolution object reconstructions overall. So here we'll use this reconstruction or this auto encoder to jointly optimize the patterns which belong to the physical imaging formation domain and reconstruction together. So so this is a joint optimization approach. So in the following, I would like to go a little bit more detail. So here is the image. First, take a look at the image formation. So let's say that X is the object and G is the mass, is essentially the pattern. And then we essentially will first do the convolution, and then we do the subsample of that. So we call that subsample convolution of this part. And then we finally add the noise, and then we get the B plus, which is the measurement. And then if we write that into the matrix format, then we have this expression on the right-hand side. And then this phi is the measurement matrix, X is the object, and B plus again is the measurement. Now, for the image reconstruction, the conventional approach is using the iterative optimizations. So basically, is this optimization approach, and then typically we will use some kind of regularization, and then illustrated by this item, the second item here. And then the psi here is basically an operator that can transform the object into some sparse domain, right? So, so this works very well, but the problem is that it's relatively slow, and also this psi is usually empirically designed, so it may not reflect what the data is, right? So it's empirical design, it may not be optimized. So what we're thinking is that we can improve this through a data-driven approach. So we use Easterm to basically to learn this site, and then also take this Easterm as an opportunity to make this reconstruction much faster because it's a neural network, it doesn't require many iterations. So this is basically a compressive sensing-based neural network. And then we use data-driven to learn the recognition term. And also because this is the neural network, this actually enables joint optimizations of the mask, basically the pattern here for each block, as well as the reconstruction algorithm. So this is the advantage of the Easterm. So and for the Easterm, basically we will be able to learn this side, right? So this block here shows the detailed implementation of the Easterm. So it basically replace the iterative global optimization into a phase-by-phase neural network. So basically the entire system is unfolded into many phases, and in our case we use 9 different phases, and for each phases the original input will be converted into some kind of domain, and then transferred back into the original domain. And then this f and f minus 1, it is the transformation, and essentially we try to learn this f. Basically, this f will convert the original image into some kind of sparse domain. And then we use the loss function. This is MSE, and also we have the constraint. Basically, it's the f to convert the image into a sparse domain, and then f minus 1 converts back. So we have this constraint here, f minus 1 operate on f and operate on the object should go back to the original object. So this is the constraint. And then we use this as the loss function. And then, so within this Easterm, we will be able to construct an auto encoder. This will simultaneously optimize the illumination pattern and reconstruction algorithm. So let's take a look at that a little bit more detail. So on the left, it is the original image. Let's say it's 256 by 256. And then using the block by block sampling, we will be able to do it very fast. So, but because it's block by block, right? So each block, we only have one measurement. So the measurement is relatively low resolution. So here, for example, if the block is 4 by 4, then the measurement becomes 64 by 64. We can see that is low resolution. And then we feed this into the Easterm, right? We feed this into Easterm, and then we will be able to obtain a high resolutions reconstruction. And then we can compare with the ground truth and get the loss. And then we backpropagate to update the parameters in the Easterm in that neural network, as well as the patterns that we use to scan the original object. So this is the entire auto encoder, and then through this f can be learned, and then we can check that it actually can convert the object into some sparse representations, right? But this is entirely data driven. So the first part is the encoder, and then the second part is the decoder. So through this autoencoder, again, both the emulation pattern, that's the mask related to sensing matrix phi, and the parameter theta in the reconstruction network, basically that Easterm can be learned simultaneously, right? So we call that this deep complexity imaging while optimized pattern scanning. So basically, it is a new modality of complexity sensing. And then this is the experiment setup. We have the light source, and then we use the DMD to implement the mask. But essentially, we do not need the DMD actually, because this is a fixed mask, right? We don't need to train the mask. But compare different masks and then to compare with their performance. And then we project this pattern, and then we scan this pattern onto the object, and then we use a photo detector to collect the image. So let's take a look at the experiment results. So here we demonstrate 4x4 subsampling, and then we compare different like so-called illuminations patterns. So the first one, it is that every 4x4, I just take the middle picture. So we call that simple dropout. And then the second scenario, it is, let's say that 4x4 block, it is uniform. So it means that every 4x4 block is averaged into with the same weight for different pixels into a single point. So we call that uniform pattern. And finally, we have the random pattern as well as the optimized pattern. So below, we have a ground truth, and then the first row is the full image, and then the second row is the zooming wheel, right? So we can see that for all the different types of wall measurement, no matter what kind of pattern we use, we can see that the resolution is poor, right? And then after that, for each of these patterns, we individually train a neural network, and then we can do the reconstruction. And then we can see that using the optimized patterns, it gives the best result. And then we further compare the PSNR as well as the normalized resolution of the reconstruction. And we can see that in the optimized pattern compared to the random pattern and uniform pattern is the best, no matter in terms of PSNR and the resolutions, right? So finally, we also compare this with the conventional switching, we call it switching mask-based single pixel camera. So this is a ground truth, and this is second row is our second column is our method. The last column is the switching mask-based single pixel camera. It's a conventional approach. And then we can see that their performance is pretty much similar, and the same in the experiment. So by the way, the second column and third column, they are the reconstruction through these two approach. And then we see that compared with the conventional single pixel camera, our PSNR and pixel resolution, they are similar, but the acquisition time is orders magnitude faster because we no longer need to use the DMD, which is slow. Even though we use 22.7 kilohertz, we consider as slow, but using the imaging, the scanning approach is we can do much faster. So finally, I would like to take another 2 minutes to discuss some more work on top of this work. So in the previous case, we are using the autoencoder based on Ethernet to just simultaneously optimize the mask and the reconstruction network. So to further improve this, to improve the efficiency, we think that we should make the sensing matrix, which is related to this illumination pattern, and the sparsity basis, which is related to this operator F. So these two should be as incoherent as possible. But in our original this framework, we do not force this incoherence. So the Ethernet itself does not explicitly enforce this incoherence. So what we think is that we can add another layer of this to introduce the incoherence optimization module. So this can maximize the Jensen channel divergence between this sparse representation and this sensing matrix so that we can enforce the incoherence. So this is basically a adversary framework. It can be used to maximize the incoherence. And then indeed, we show that the simulation results for different reconstruction network. And then if you look at the last two columns, so this is Ethernet plus, and then here we have the adversary deep compressed image. We can see that the performance can further enhance here. So finally, I would like to summarize. So here we have demonstration that a new imaging modality that can combine the scanning technique and compressor sensing to increase the imaging speed. And the end-to-end deep compressed imaging model, it can simultaneously optimize the physical scanning parameter and the imaging reconstructions algorithm. And finally, we also propose a adversary framework to further increase the efficiency of the data acquisition and the performance of the reconstruction model. And finally, this is my funding source, NSF, NIH, and Both Welcome Fund. And thank you very much for your attention.
Okay, thank you so much, Professor Yang, for your nice talk. And we have a few questions from the audience. And the first one, I want to ask a question about, as a speed-driven model, STA Easter night is proposed for the compressed imaging. So I'm wondering, like, the optimized. The loss function you mentioned here, yes, the loss function you mentioned. How to choose the loss function?
So basically, for this work here, the loss function it's composed of two. The first one is basically the MSE. So basically, is the difference between the reconstruction and the ground truth. I think everyone has that. And the other item here is something related or somewhat similar with the conventional one, where we have the regularization term. But here we use the constraint because in this Ethernet, in each phase, we first perform a forward transform of the original object into some kind of sparse domain, and then we transfer back, right? So these F and F-1, they are implemented by the neural network here, as I saw in the upper block. So we want to make sure that this forward transform and backward transform, they kind of they are consistent with each other, meaning that your forward transfer and then backward transfer, it should go back to the original one. So this is the constraint, and then thus we use this constraint as a loss function as well. So we try to minimize this inconsistency, right?
Okay. So another question is, are the image subsamples involved in the convolution overlapping?
Sorry, can you repeat that question one more time?
Okay. Okay, the question is about overlapping.
Right.
As the
so
image
here,
subsample, yeah, you go ahead.
Sure, yeah. So here we do not have overlap, right? We actually have also done one experiment, which I didn't show on the backup slides. So I think it's great to answer this question. So here we show that we have the length of the pattern. So for example, if we look at one of these traits, for example, let's take a look at the blue curve, right? The blue curve is 6.25 undersampling, which means 4x4, right? So for 4x4 subsampling, the best scenario is the 4x4 pattern size. So there's exactly no overlap. The reason is that if we have some more overlap, different measurements, they are no longer orthogonal to each other. So somehow their performance slightly drops, as you can see here. Though it's very similar, either 4 or 5, they're similar, but nevertheless, the 4x4 without overlap is the best. So,
Okay. Okay. Okay, thank you again, Professor Yang. If you have more questions, please contact with Professor Yang regarding to his presentation today. Okay, let's have our next speaker. Thank you again, Professor Yang. Let's have our next speaker, Professor Shao from Xidian University, China. Professor Shao, are you here?
Yeah.
Okay. Can you share your screen?
Okay.
Okay. Before Professor Shao.
Screen?
Yeah, I can see you, but I cannot see your screen.
Oh, really? Oh. Can you see it?
Yes, I can see it and I can hear you. Okay.
Okay.
So I will briefly introduce Professor Shao. He is currently the executive dean of the School of Physics and Optoelectronic Engineering at Xidian University. His established research includes topics on computational optical imaging, optoelectronic imaging processing, and pattern recognition, development and testing of the photoelectronic instruments. As a pioneer in computational imaging, Professor Shao will present us his vision on computational imaging. Okay, let's welcome Professor Shao. The stage is yours.
Okay, thank you for Dr. Wang's invitation. Thank you, Professor Gu. My topic is computational imaging and its fundamental issues. This is my outline. First is an introduction. God said, there be light, and there was light in Bible. So light as an important information carrier for sensing the world. There are many applications in remote sensing, intelligence transportation, mobile devices, and medical imaging. But we can see that for some time we acquisitions information in imaging, but sometimes we can see some information lost. First in spatial domain, our world is 3D world, but after projection, only 2D, two-dimensional information we got. And the second, in physical domain, many physical many physical like face, spectral and polarization, but after imaging, we can only get the intensity, and in the information domain, the signal is analog signal, but after next sampling and quantization, we get the digital signal. So the date changed. So in many applications, advanced applications acquire further detection range, higher resolution, wide field of view, strong environment adaptation, and a smaller optical system for photoelectronics imaging. For traditional photoelectron imaging, it reaches the theoretical limit. With the development of digital signal processing technologies and computer technology, the computational imaging technologies arise as a moment. This is a traditional approach, and no approach we can the information can encode. After decode, more information can pass through the channel. So it's the information driven. This is a research status of computational imaging. At the end of 20th century, Stanford University, Columbia Columbia University and MIT, they do some research work about computational imaging. And after that, in China, as a promoter, I organized a symposium on computational imaging technology and applications with more than 100 research institutes in China from 27th and to 2020. And I also organized the first computational imaging conference, CITA, in this September in Hangzhou. Now I give a definition of computational imaging, integrating optical mathematics and information technology. Computational imaging takes information transformation as a criterion and focused on global optimization design for full imaging link, in which the information coding technologies is introduced to realize the information channel expansion, domain promotion, and information acquisition ability improvement. There are three key points. First, it changes the traditional optical design as a abbreviation optimized in traditional optical design. In computational design, we will introduce the information criteria. The second is following the global optimization for full imaging link, include transformation media. And the third is applied active and passive information coding in breakthrough imaging limit. We can see that like the transmission media, like the air, water, is actually is a passive coding method. So after give that comparison to traditional imaging, is what you see is what you get, and after computational imaging, what you get is more than what you see. To CIT, computational imaging is driven by two innovations. It's a higher development speed and potential than traditional imaging technology. The first is a two-dimensional photon innovation and beta innovation. There are two realization approaches. One is digging deeply from acquired information. The object after we get the original information after interpreting, for example, enhanced image enhancement and scattering image, etc. We get a new object information. And the second is upon this desired information channel. The object after information expansion, for example, coded exposure, polarization, imaging, etc. More information, more dimensional information, we get more object information. Our goal is a high resolution, further range, wider field of view, a smaller system, and a stronger environmental adaptation. The second, I will introduce fundamental issues. The first is imaging model. The problem of the existing imaging model is actually a linear model. We use convolution method in the imaging progress. The linear description lead approximation error is the first, and the second, information dimension loss cost the real number transformation, and the second is optical imaging process and imaging processing is deserved. Now we give a new imaging model. It's a linear and complex field transformation. Maybe it's can written like this, but I don't know exactly how to what was the form. The new imaging model, we hope it can work singly, just like this system A, B, C. It work singly. Everyone have low resolution, maybe have low resolution, but sometimes we hope this system what collaborative work together. So we hope we can have higher order Easterm in this equation. It can we can get a high resolution image, just like human vision. Two eyes vision is better than any single one. The second is a high resolution. The high resolution, the reason of restriction, first is optical diffraction limit, and the second is limited aperture size of optical system, and the second is the detector for performance limitations. We give some method list on the right side. This is Abbe diffraction limit. We know that, and the first method maybe beyond the diffraction limit is expand the spectrum. All these methods always use in macro, always in how to expand to macro field is very hard, I think. And the next is super large diameter telescopes. The telescope manufacturing limitations like huge system scale, long production cycle, difficult to assemble, and adjust, high cost and poor environment adaptability. So the actual surface profile accuracy decrease, and the OTF and the image quality decreased. So we want to make a rough surface with low precision, but we can get a high resolution image. And this is synthetic aperture imaging. It's just like a Fourier telescope, etc. But the background is need. This is advantage. The first is difficult to installation and adjustment and high cost. Fourier telescope, the background light influence series. Another is subpixel displacement. This also used in cameras. And high resolution is a new detectors. We hope the detector is not like the traditional detector is a uniform sampled. We hope a non-uniform sampling is breaks the Nyquist diffraction limit. And the third is further detection range. Industrial design is difficult to achieve global optimization, and the optical system is complex and weak recovery ability with low SNR signal and scattering medium influence. We give some limited reason. The signal from high dB to low dB. So we always can process the signal with 3 to 5 dB to detect the object, but if it's lower than 1 dB, 0 dB, even negative dB, how to process it is a challenge. And the optics is always complex. There are many energy lost, and the common detector cannot obtain ultra low signal SNR signals. And another limited reason is the medium, like cloud, smoke, and hazy environment. If we can optimize for full imaging link, maybe we can save some dB for just like this. Is a global optimization. We can get a higher. We can get a better signal, and this is simplified the optical system. Our optical system is always with many glasses. Some newer lenses appeared recent years, and the scattering imaging. Scattering imaging, we hope we can get some image invisible to visible, just like sometimes we always see some spectral like this, but we can resolve the image like this. But there are some limit, like spectral wide, narrow to wide. The spectral quality lower. We can see that the correlation profile from the wider spectrum. This is a narrow spectrum. Actually, it have a good autocorrelation profile, and the field of view is also limitation. We can expand the field of view, and the surround background light is also affect our application. This is some method. This is the result we researched, and it's very hard to dynamic scattering problem like water and smoke, and this is polarization imaging. Sometimes we can use some another physical characters like polarization to enhance the image quality. And this is one work is 3D polarization imaging. This work we can take one picture and we can get a 3D image just like this. Maybe some it has it's maybe can use in mobile phone and auto driver. And this is a scenery. We get a 3D polarization imaging. Okay. The wider field of view is a high resolution, and the large field of view is drift each other, and it produces massive data. This is the limited reason. We designed a camera. The field of view is very large and is very have high resolution. The results show like this, but it's produced many a huge amount of data. The last is a smaller optical system. The traditional optical design is driven by aberration correction and lead to large value and complex structures. The lens always like this, many glasses in this system. The one method is optics image draught design. The processing is imaging restoration algorithm be part of aberration correction pressure of optical system design, then simplifies system structure, increasing energy transmits and reduce sampling difficulty. And this is one report. It's use high quality neural narrow optics. It's a great work by Preston. Okay. And another is a crowd detector. If a crowd detector is it can minimize the optical design. Last, I give the conclusion. The first is CI is used for development of photoelectronics imaging technology. The combination of information and physics will expand the limit of the photoelectronic detection. The second is the definition of CI, and the third is a fundamental theory of CI urgently need the development, and the imaging model need to improve. Extraction method of a low SNR signal and the new detector technology will promote the development of CI. This is my research team. Thank you very much. That's all.
Okay, thank you, Professor Shao. Thank you for your wonderful, insightful overview on computational imaging regarding to the speed, field of view, resolution, photo numbers, and etc. And because due to the time limitation, if you have any questions from the audience, if you have any questions regarding to his Professor Shao's presentation, please feel free to contact with her in person. Okay. Thank you, Shao. Thank you, Professor Shao. Okay.
Thank you.
Okay, our next speaker is Professor Chen Xi from Peking University. Peng Xi from Peking University. He is currently the Deputy Director of the Department of Biomedical Engineering, School of Engineering, Peking University. He is a distinguished researcher in super-resolution microscopy imaging, biomedical photonics, new microscopy techniques, and the applications in biomedicine. The title of his presentation today is Super Resolution, an Adventure on a New Dimension. Let's welcome Professor Xi. The stage is yours.
Thank you, Dr. Wang, for a kind introduction. And I'd like also to give thanks to Professor Minggu and the organizing committee for inviting me to be here today. So my name is Peng Xi from the College of Future Technology in Peking University. I am also jointly affiliated with the Department of Biomedical Engineering in the College of Engineering in Southern University of Science and Technology. And so today I'm going to talk about two recent progress in our group. The first one is the polarization theme. And I think all of the audience have read about the famous sci-fi novel entitled The Three-Body Problem. Inside this novel, the author proposed an method that the aliens may attack our people, which is the dimensionality reduction strike, 降维打击. What is dimensionality reduction strike? It means, for example, if we were able to join a conference offline, face-to-face, then since I practice Kung Fu every day, like Li Xiaolong, you will be threatened if you insult me, right? But for this online process, even I have a super high Kung Fu, I cannot hurt you because now my dimension is reduced from the 3D into a 2D image. So you're like watching a movie right now. So for super resolution, it is actually indeed viewed from a new dimension. For example, there are a type of super resolution technique which Professor Shao has just briefly covered, which is single molecule localization microscopy. In this single molecule localization microscopy, the problem is that when 2 points get close by with each other, then they emit light simultaneously. We cannot separate them, but we can separate them in time, meaning we let them blink, and then we see each blink blobs, and we get the location of that. We get and the super resolution. Another distinct technology is called stimulated emission depletion, which is to separate those molecules in spectral domain. For example, I can modulate the peripheral of these molecules to be another color, which is to emit the stimulated emission. And then all in a sudden, I can separate the spontaneous emission, which is in the center, versus in a close by emitter, which is not in the center, but emitting different color. So in that way, I can generate super resolution. And you will find that it's actually when you were able to introduce a new dimension, then the close by molecules that I mentioned, when we give it a new dimension, then we can give it a new distance. And this so-called distance can be easily separated. So You can also combine the temporal domain and the spectral domain together to achieve better resolution. And being a physicist, we're looking for new dimensions that we can work with, just like Professor Shao has just mentioned. So we take a look at the Florfer's dipole orientation or polarization domain. We find that when we are image biological specimen, it is usually transparent. So what we do, we label fluorescence probes on top of that, make it visible. And since the optical fluorophores were targetedly labeled onto the specific subcellular structure, when we see the fluorescence, it is equivalent that we see the underlying structure. So if their organization or the polarization of this fluorophore is organized in such a way, we also can derive the information that our subcellular structure is also arranged in the similar approach. And briefly, let me describe the principle of structured illumination microscopy. So we are using essentially an Maury pattern to modulate this high frequency into a low frequency domain. Why do we do that? This is because when we are monitoring, when we're shifting it to a low frequency domain, we were able to see it using our optical system. Let me give you an, I will pause the broadcast for a moment and give you a live demonstration. So you can see me, right? So here is two structures, two patterns. So with one of them embedded with characters. When I overlap them, you will see those stripes. But it's only when I get this modulation correct that you are able to read the characters on top of that. Okay, this is the principle of super resolution structured illumination microscopy. And let's move on. So since we understand that the structured illumination, we need an sinusoidal modulation in spatial domain. And in this polarization, when I rotate my when I rotate my linear excitation, polarization, then the response of this dipole will also share an sinusoidal. I can combine them together to make a super resolution polarization, super resolution imaging. So let me first show you some of the results. So this is a wide field image. And with the structured illumination, you can see that we can boost the resolution by twice. But with my polarized super resolution technique, you were able to tell that this has a green color, which means its polarization is in this direction, and this filament is in this direction. So there essentially it's organized in the perpendicular direction of its propagation. So in collaboration with Professor Shanghai Dai, we found that the orientation structured illumination can also be embedded in an structural manner, like from minus half pi to half pi repeatedly. And when we use the same principle to extract the information from this giant matrix, we find that surprisingly, we were able to tell the orientation of each pixel. And by doing that, I've shown you this is actually the microtubule labeled with GFP. And in collaboration with Professor Xiaowei Chen in our college, we were able to visualize the evolution of this microtubule over time in a very fast manner. And I believe most of you have also watched this movie, which is a myosin, a cargo protein, and to move across an actin filaments, which is quite like an acrobat walking along the ropes. But here, what we want to do is we want to fix this acrobat and see how he steps onto these ropes. So we fixed the myosin, and this is in collaboration with Professor Xiangdong Li in the Institute of Zoology. And we see that the actin, they are floating and drifting, and you can see long actins as well as very tiny, very small actins. For those long ones, you can tell easily its direction, but for those tiny ones, it's very difficult. But thanks to our technique, we were able to extract the polarization information for this actin, and we find that for actin, it's always along its propagation direction, and the moving direction and the dipole orientation will correlate very well with each other. And this animation is when you give it sufficient ATP, means energy. But if you give it insufficient ATP, the actin will perform like wobbly instead of this floating and drifting. And we also know that in the super resolution community, Professor Xiaowei Zhuang is a pioneer. She is in Harvard University and the HHMI, and she won the Breakthrough Prize in 2019 for her work in the super resolution fluorescence microscopy. And one of her representative work is about the organization of actin and spectrin. So by using this dual color storm, what she visualized is that this actin and spectrin were organized in a periodical manner with period around 190 nanometers. So because we have the pre-knowledge that actin will be cut into small pieces like 2 nanometer by the adenosine, and she proposed that the organization of actin would be like rings, which gives an end-to-end structure to organize this spectrin, whereas the spectrin gives the period of 190 nanometers. Is that true? In order to validate this question, we collaborate with Professor Zhang Yan in the IDG McGovern Institute, Brain Institute, and we did the same experiment. So from this part and this part, you will find that on the dendrite, the organization is in this and this direction respectively, which means that the labeling for the actin is along its propagation direction. So if the end-to-end model is correct, we should be able to see the same blue or green color along this part. But we were able to see that there are period, and their period is around 184 nanometers, but the color is purely red. If we read from this table, we will find that red color implies that this is in this direction. So we modified the model and to be like a side-by-side organization, and this work has been highlighted by Nature Methods. So next is about spectrum and polarization optical tomography spot. We know that cell has a rich is an self-walled with rich subcellular organelles respond for different roles. And usually when we would like to research on their interactions, we use multicolor fluorescence imaging, and each color we label one organelle. And but if you look at this fluorescence proteins spectrum, you will find that they were heavily overlapped. So the state of the art is that Professor Eric Basic and Jennifer Lipkotin-Schwartz, they published on Nature using multispectral imaging and linear unmixing. They were able to separate up to 6 different organelles and see their interactomes. And but the underlying problem is how can we label different organelles when their chemical compounds were similar? So when we're trying to address this problem, we were thinking, can we shift the paradigm by using one single label to label all the organelles altogether and then separate them? But if you see the image of this cell, I think you probably will give up this idea because it's highly messed up. So with the once again with the power of super resolution microscopy, we were able to make this image much clearer, and by using the now red we were able to label up to 10 different organelles simultaneously. And with research on the chemical sensitivity and the mobility sensitivity for this glycerol lipid, sphingolipid, and cholesterol, we find that they were different in both chemistry and mobility. And with that, we were able to separate these 10 different specimens of this how to say different groups of lipid organized organelles, and we find that in general with the emission ratio drop decreases, the modulation depths will increase. However, you will also see that for lipid droplet, it has both low emission ratio and low modulation depths. And for ER and the nuclear membrane, it has both high emission ratio and high modulation depth, which suggests that sophisticated lipid interaction happens. And this is in agreement with the mass spectroscopy, but mass spectroscopy cannot give you the temporal resolution for that. And with this 2D plot, we are trying to separate all these 10 different organelles in association with the computer deep learning technique. And this work has been highlighted by a series of medias. So we're trying to open up a new area of single cell multi-omics, which combines the organelle interactome, lipidomics, proteomics, and possibility genomics. So in conclusion, the super resolution is vision from a new dimension, and here I described the PCM and the spot. And I'd like to thank my collaborators and students and the funding support from NSFC most, and also Beijing NSF. And that's all for my talk. Thank you.
Thank you again. Thank you for your wonderful presentation and very dynamic talk and a nice demo on the basic concept of PCM. So due to the time limitation, for the audience, please feel free to contact with Professor Xi in person regarding to this presentation. Thank you again, Professor Xi.
Sure. Thank you all.
Okay, let's move on. Our last but not least speaker is Professor Akka from my alma mater, VU University Amsterdam, Netherlands. So, Professor Akka, I'd like to mention that it's worth noting that she is one of the few researchers in the world to study portable, economical, and compact optical coherence tomography system. So the title of his presentation today is Integrated Optics in Medical Application. So welcome, the stage is yours.
Thank you. Thanks so much, Daisy. Thanks for the invitation as well. So I'm going to open my talk. I hope you can see it now. Is it You see it all?
Yeah, I can see it and I can hear you clearly.
Okay, perfect. Thank you. Thanks again for the invitation. I'm just trying to, yeah, okay, now it's perfect. Yeah, my name is Imran Avcı, as Daisy said, and I've been an assistant professor at the FU University of Physics department for a while. And I've been working in the field of integrated optics for more than 20 years, and I started applying medical into this field for the last 10 years, let's say. So I will start off with giving you some idea about what is integrated optics. If my slides move, sorry. So, yeah, basically integrated optics is one of the fields which is growing with the high speed, let's say. And the nice thing is it's very much similar to integrated electronics. You know it from your cellular phones even, but there we use electrons. But when we go to the photonics, integrated photonics, that means that we switch to photons. And the beauty here is photons are quite faster and they're massless, so which means that they're also energy efficient. So that's why there's a big drive towards making things on chip using photonics. There are even photonic processors, neural network systems that people start working with. The idea is making everything small, functional, massively producible, so that the cost is reduced. And the main building block is the waveguide, an optical waveguide. It's very similar to an optical fiber, but now instead of 3D, we are in 2D. So I will show you some examples of the fundamental components. So these components, you can buy them from Tor Labs or from another vendor. But the idea is with integrated photonics is we can also make the similar ones or sometimes even better ones on chip. I will explain you why it's important later. So as I said, the first component is an optical waveguide. Then we can make using these waveguides lasers, even comb lasers, optical frequency comb lasers at a very tiny size, extremely small size. We can make splitters, extremely efficient broadband splitters, interferometers, spectrometers, modulators, and photodetectors. If you look at that, you see that all these things you can make a very nice a design, a very nice optical setup on a small scale. So if we look at the applications, there are several things. I just listed 4 of them here, but it's a very highly growing, rapidly growing field. One thing is medical imaging, and the other thing is still in the medical field is optical sensing. People have been using photonic integrated circuits for I think more than 20-30 years in telecommunication. This is an enabler for us, and also quantum optics, which has started as one of the recent fields that people start investigating using this technology. And as I also said, there are photonic processors which are going to replace in the future the electronic versions of them. So this is a chip that you receive from a vendor, and this is how it looks like when you shine it with the red light. So I want you to have the feeling that what a photonic integrated circuit looks like. It's very tiny, even though it looks bigger here, it's very tiny. You shine it with the red light and you see how the light is propagating throughout the structure. You see all the details. And if it's a low loss structure, you see this the light, which is starting off from one part, ends on the other side. So this means that this is a very low loss structure. That's a very good sign. So, and the basic building block, as I said, is an optical waveguide. It's a cross section, looks like mainly a rectangle in contrast to an optical fiber, but it has a low index material, high index material, and the light loves to travel in the high index material, so we can guide the light very efficiently within this little square structure. But making it is quite tedious, so you need to follow a very strict procedure. You have to be very careful. We are talking about nanometer scale things, and even a nanometer scale change at the surface of this little square shape will cause you lots of loss. You will lose lots of photons. So you have to follow a procedure. And yet another thing is you have to do it in a professional environment, advanced laboratory called clean room. So that is. If you put it that way, it's kind of a drawback, but the outcome is amazing. So we are willing to pay for it. So the first thing is optical imaging. That's what we can do with photonic integrated circuits and how we can apply it to optical imaging is I did it through my PhD, and it's a very nice technology, optical coherence tomography. You see in 3D structures with high resolution. but there are certain problems. That's why we choose this technology to make it smaller. So the basic building block, sorry, the basic function, I assume it has been explained several times during this conference, but it's very basically saying you have an ultra broadband light source to make it low coherent, and you split the beam, and then you send one arm to the reference side, to the other arm to your sample, and then you collect the light back and you send it to your detection site, which could be a spectrometer or a single detector, depending on which type of OCT you are using. And when you scan the mirror over here, when you scan the mirror, then you can get a three-dimensional image of the surface. But it's not just about the optics. You also need to combine it with a quite tedious post-processing technique. So you acquire the data on the spectrometer side at different depths. You get a different frequency of oscillation, interference signal, and you take the inverse Fourier transform, and then you reconstruct the points which are reflecting off from the surface at different locations. So you get all the data, you combine them, and you make kind of a reflection map, and this will give you the internal structure of the tissue or the cell that you're looking at. So as I said, there were some quite issues with OCT. Okay, nowadays we can even make them cheaper, but the quality is also dropping in most of the cases. And if you want to buy a commercial OCT system, average cost is 60,000 euros, and it can go up to 120,000 euros depending on the equipment they use. But if you look at the ultrasound, which is very similar to OCT, but they use sound waves instead of light waves, we see there are handheld probes. Even when you go to your doctor, they can even check you very quickly with a handheld ultrasonic device, and they cost mainly not too much, around 5,000 or 6,000 euros. So our goal during my PhD was to make it small so that it will cost quite low. It's going to be a very affordable technique for developing countries even. So we started off with the idea of spectral domain OCT because it's, in a way, it's a little bit more harder to stabilize on an operational card because you have components which are very sensitive to movement. I know it because I'm also in the department of biomedical imaging, where we have several OCT systems, and we need to take them from our section to the medical field. And even when you carry them, you see that all the alignment is gone on the way because you are going through bumpy corridors sometimes. So we always need to align it. So one beauty of integrated optics is once you make it, it's very robust. There is no way of changing the alignment. So in this case, as I said, we work with spectral domain OCT, and the main component that we used was an optical splitter, on-chip splitter, and a spectrometer. That part is quite tricky if you want to make it off the chip. But the rest during my PhD they were completely off. So we used an external light source, some external scanning unit, an external light scan camera, but it worked pretty well, I would say. So if you look at the individual components, the spectrometer is the core building block of this type of OCT system. So for that we use arrayed waveguide gratings. So it's basically very similar to a diffraction grating, but it's a planar version of it. And the operation principle is you send the light, it diverges, and then it couples into the arrayed waveguides, which are arranged in such a way that you create a phase difference between each, and this is constant. And then when they reach the other part, they recombine and they constructively interfere, and then you receive the signal at certain port. And when you change the input signal, then you see the color of the light is going to another channel. So here, the important thing that you need to remember is this: the design. Two design parameters are very closely related with the OCT performance. One is the resolution of OCT, which is the spacing between these channels. That gives you the depth range. Smaller the resolution, better the depth range, which means you see much deeper in the tissue. And the bandwidth is defining the depth resolution. That means how well you can resolve the structures within this depth. These two things keep in mind, and then you can design a spectrometer on chip and you can make really nice OCT systems, but it's very tricky. Because reaching both a high resolution and also a large bandwidth is quite tricky. You need to apply some smart tricks there. which I'm not going to talk today. So miniaturized beam splitters that we use is also a special type, which is a diabetic beam splitter. If you buy an optical fiber splitter, they are mainly made out of directional couplers, or some of them are fused fibers. They claim they can go up to 100, 150 nanometer of bandwidth. It's important because what we saw before is the bandwidth is defining our resolution. So we need large bandwidth to be able to resolve small structures. So for that we borrowed an idea, diabetic couplers, and there you make the waveguides. This is the top view. You make the entrance waveguides in terms of width quite different, and they ended up the same. So this will give you a 3 dB 50-50 splitting ratio in the end. And by doing it so, we made sure that we only excite one system mode, and the system mode, since this is an adiabatic system, it will eventually split into two. So adiabatic means you need to make it long. That's the only drawback here, but it's working perfectly. I will just show you. We made it over 150 nanometer bandwidth, and the splitting ratio is, as I said, 50% for both arms. So we equally distributed the light between arms. And we use this optical little chip in the University of Vienna, and we demonstrated that it's working pretty well on volunteer skin. So you see several different images that we took, and the resolution was 7.5 micron. It's very close to what you can buy nowadays. The depth range is 1 millimeter. It could have been better, but now it's 1 millimeter is enough for skin imaging, let's say. And signal-to-noise ratio was 74 dB. As I explained to you, it's less than commercial systems, but the main reason is the loss, input-output loss, and also the little loss that's created through when you're making the structures, this nanometer scale losses. So there are, even nowadays, there are quite new examples of such systems. They are working pretty well. So if you check the literature, people are improving the fabrication, and they're going quite high signal-to-noise ratio. So the next thing is optical sensing. This is another thing that we are doing in my group. For early cancer diagnosis, we are working with optical biosensors using integrated optics again. An optical biosensor is basically a device, any device that converts the biological compound into a measurable signal. What that means is there is something happening in the environment, and you want to make sense of the signal, of the change that's happening around you, and you want to measure it. So this is kind of a transducer, receives the data from environment and then transfers it into a logical signal to you, either electrical, optical. That's something that makes to you that you can really record and do something. So this is a state-of-the-art optical biosensors problem that I try to show you here. So this chip, although it looks quite large, this is basically an integrated optical chip, and there's underneath you see a cavity. Most of the time we use a cavity because cavities are much more efficient in sensing. And these are little optical waveguides. What you don't see here is the light source and the photodetector. And there's also a temperature controller that you see. And the main drawback here is the coupling efficiency, how you can couple the light in and out. If you want to make this disposable, that's the problem. Because you want to use it once, let's say for blood samples, and you want to throw it away. And the next time when you put the next chip, somehow, some way, you have to align the light again and light in and light out again so that you can measure it. The problem is these are micron scale structures, so your alignment is also in the sub-micron, at least, accuracy. This is costly. That's why you don't see lots of optical biosensors in the market. And even though there's a huge potential, that's a big problem. So with one of the projects that we received recently, we are going to tackle this problem by making everything monolithic. And we also follow a different approach here. We will put our laser sources, our detection, sensing elements and the detection part on the chip by using optical frequency comms, self-referencing sensing elements, and by using two of these optical comms, we are also planning to make it like a heterodyne detection scheme so that we can even reduce the cost of the electronics afterwards. Because you read the data, but you need to convert it to electrical domain so that you can read it. So eventual goal is to make this chip 2 to 3 euros per piece. So it's multiplex, sorry, that's one thing I forgot to say, which means you can put different droplets. You can do the simultaneous measurement from a single person, a single patient blood sample for different biomarkers. So that's very critical, that's very important, because from one biomarker you couldn't say anything about the disease. So you need multiple cross-checks. And this is going to be disposable, although the laser and the photodetector is going to be trashed. You don't care because it's also cheap. And for that towards goal, we made an optical frequency comb. It's a mod-locked laser, actively mod-locked Fabry-Perot laser. And through driving the current, it's not like the microcombs that you see nowadays using a micro ring laser, sorry, a micro resonator, and then they put the input a pump laser. So there's no external pump in our case. It's just electrical in, electrical out. That's the beauty of it. And since this is very carefully, very finely, we can change the temperature and also the driving current of the laser. We can make two lasers almost exactly the same. So we can make them slightly shifted in frequency so that we can make heterodyne detection possible. That's the beauty of the idea. This is how it looks like, the bandwidth wise. It's centered at 1545. For the sensing element, as I said, ring resonator is very popular. So we're also using ring resonator, but we add a little twist to it. I will show you in a minute. A ring resonator is just a closed loop, it looks like. So the light comes in, it couples in, and it's standing wave. So you create a kind of a standing wave pattern, and then this light stays there for, in certain cases, 1,000,000 times, and which increases the interaction of light with the analytes that you're putting on. So we also need to know that there's light traveling inside this little circle, but some part of the light is traveling outside of this circle, which is the evanescent field of the light. That is very critical, very important for optical sensing. This part of the light we use to detect analytes around it. And for that, we need to engineer the waveguide so that the tail of the light should be large enough so that we can capture more signal from the analyte, even though there's little bit of it. Yeah, that's important. So what we look for is the shift when there's a change in the environment. And this is the transmission response of the ring when there's nothing, and if there's when there's a binding happens, when there's a molecule around it, then you see a shift. So this shift that we are after for. So as I said, we are adding a little bit of a twist. We use double ring resonators in this configuration, and then we only send the analyte to one of these arms, half even, one of the arms. And what it does is basically it creates an internal reference, internal self-referencing point. This point doesn't change, this peak, which is coming from the top ring, and that part is shifting when you change the refractive index. So we don't need to be worried about the gradient of the temperature because they're quite close by, very small scale rings. And also if the temperature drifts, we also don't care. And as I said, that heterodyne detection is the next nice thing, which I already explained, using two frequency combs very closely in the frequency domain. What you can see is the difference in their frequency will give you a signal in the RF domain. RF electronics is quite cheaper nowadays. It's a very established field, so that's the beauty of it. In the infrared domain, everything is still expensive. If you want to make a cheap, affordable sensor, so that's why we are aiming for RF domain to make the electronics also cheaper. Lung cancer is our first goal. So we are looking for lung cancer biomarkers in the bloodstream because it's one of the most fatal cancer type. And for the specificity, what you need is, okay, so far we just discussed the idea, ring resonator, something happens and then we see a shift, but this shift could happen for any reason. That could be another molecule which is in the neighborhood of the evanescent field, and you need to make it very specific to your molecule that you're looking for. And the only way to do it is the functionalization of the surface with a certain protein, and this protein could be anything. And in our case, we are going to look for the lung cancer antibodies that will be provided by a big name, Sangenics, working in the field. we will try to find, we will try to use this as the material that will cover the surface of the ring. We will try five of them, because as I said, you need to cross-check. Just one biomarker is not enough for you. We will follow a very simple procedure, chemical procedure, and then afterwards we will see that whether it's working on the blood samples that we acquire from the lung cancer patients. So this is what we are working on nowadays, and my eventual goal is to be able to make everything affordable for everyone. Still, 2 to 3 euros is not affordable for many countries, but still in Europe it's something very, very affordable, to be honest, and it's reducing the burden on the medical side, and that's why we are really trying to do it in this way. I would like to thank you all for listening to me. Probably I exceeded my time. I'm really sorry for that if that's the case.
Okay, thank you, Professor Arka. Thank you for your wonderful presentation. And I have one question for you about your on-chip OCT. So from the benchtop to bedside, what's your perspective on the clinical translation of the affordable on-chip OCT?
Clinical transition. Yeah, basically, this is the same thing that you do with the bulky OCT system. There's no difference because it's going to be, the final goal is not using it in the clinics, but mainly at home, home care, point of care kind of things. So you imagine that you have a mole on your skin, and you, instead of going to the medical hospital, what you will do is have one of these portable systems and try to look at it by yourself every day, check what is going on. So the idea is that, and also on the developing countries, if you have such a tool, that will save lots of lives. That's the idea. So I'm not really concerned about the clinical transition, to be honest.
Okay. Thank you so much. Thank you again.
Thank you.
Yeah. Okay. That's all for section 3. Thank you again for your wonderful participation and patience. Now we have the closing remarks.
Hello everyone. So here we are at the end of these days of talk. It was really quite exciting, and it's been really a truly great day. And I'd like to thank again all the speakers of the wonderful talks that we hear during the sessions, and also everyone who connected for today's in making this a very lively and a very participated and interactive event. So thank you so much. On behalf of the Institute of Photonic Chip team, I wish to extend my sincere thanks also to the steering committee for their advice, and to the program and organizing committee for all their work. And finally, I'd like to thank Wiley and Advanced Intelligence System, without whom this conference would not have been possible. Now, before concluding this event, we have the closing remarks from Dr. Babak Mostachi, and there will be the announcement of the winners of the poster sessions. So now we can hear the closing remarks from Dr. Mostachi.
Ladies and gentlemen, it's my pleasure to speak at this prestigious event. I hope you enjoyed the exciting talks. For those who don't know me, my name is Babak Mostachi, and I am the editor of a number of journals at Wiley. At the moment, I'm Deputy Editor of Advanced Materials and Advanced Intelligence Systems, which is one of the sponsors of this event. First of all, I'd like to thank all the speakers who presented their research here. The members of the organizing committee from both University of Shanghai for Science and Technology and Wiley have done a great job to realize this conference, and I appreciate their hard work. Special thanks go to Professor Mingu as the conference chair, and to Ms. Elena Goi from USST and my colleague Dr. Huan Wang from Wiley for the awesome event. As part of my closing remarks, I'd like to say a few words about Advanced Intelligence Systems. The journal was launched in 2019 as an open access title focusing on topics related to intelligence systems, including artificial intelligence and machine learning, robotics, automation and control, neuromorphic engineering, self-assembly, and so on. To reach out to our global authors, we have editors in our global offices in Germany, China, and Australia. The great news is the journal has been indexed in the CIE database by Clarivate Analytics in the subject categories of automation and control system, artificial intelligence, and robotics, meaning that the journal will receive an impact factor next summer. The expected impact factor will likely place AZ among the top tier of journals in the relevant fields. So Advanced Intelligence System has been a very successful journal, and there are several reasons for that, and I'll try to mention a few of them. First of all, the journal enjoys having a top quality and diverse editorial board. We have also invited many top authors from different disciplines to contribute to the journal, and of course, their papers contributed to the success of Advanced Intelligence Systems. Papers in AZ are highly visible, as we always try to highlight them either on social media or through promotional videos. We have organized several interesting special issues on hot topics such as soft robotics or neuromorphic engineering, and we have recently started a collaboration with Autorio, enabling authors to submit or publish interactive content, interactive papers, or interactive supporting information. So, as I mentioned, several papers in each issue of AZ are highlighted in promotional videos, and you can see here the playlist for all of these videos on YouTube. And also, we have collections of interactive papers on Autorio for interactive supporting information and interactive full papers. I hope we'll receive your papers in Advanced Intelligence Systems in the future. With this, I conclude my talk. Thank you very much for your attention.
So, thank you once again to Dr. Mostaci for his kind words at the end of this event. And now we move on to the poster session and to the winners of the poster competition. So first of all, I really would like to thank everyone who actually submitted a poster and contributed to this event in this way. And now the announcement. So the prize for the best poster goes to Chu-Hee Liu from Fudan University. He presented a poster with the title Signal Recovery in Optical Communication Using Optoelectronic Convolutional Neural Networks. The second place ex aequo is shared by Simone Lamon from the Institute of Photonic Chips here in the US University of Shanghai for Science and Technology, and his poster Low Power Super Resolution Optical Data Storage using Upconversion Nanoparticle. Is sharing the second place with Feng Tian from UC Davis. His poster title is Geom Scope, Large Field of View 3D Lensless Microscope with Low Computational Complexity. I also want to mention that we have two honorable mentions in this poster competition. The first one is Hui Wang from Tianjin University, and his poster, Photo Control Reversible Dynamic Bond for High Energy Solar Thermal Fuels, and Canning Zhang from UC Davis, and his poster, Deep Compressed Imaging via pattern scanning. So I would like, to really thank everyone that participated to the poster session, and really congratulations to the winners. They will receive a certificate from Wiley and also a prize as a wireless keyboard that will be sent to them. So congratulations once again. This is really the conclusion of this event. I want really to thank once again the speakers, everyone who participated, but also Wiley and all the organizers and all the members of the steering and the program and the organizing committee. Thank you very much. This event would not have been possible without you. And now we can really say that the Photonic and Advanced Intelligence System Conference is concluded for today. And I thank you everyone once again.